Hello there, and welcome to The Sleepy Scholar. Tonight's journey takes us through the deep history of Earth, from a newborn world of fire and falling stone to the oceans, continents, and skies we know today. Along the way, you will hear how the moon was born, how the first seas gathered, and how ice, air, and moving crust patiently shaped a living planet. If you enjoy these quiet explorations, consider subscribing so you can easily return here whenever you need to rest. For now, get comfortable. Let your eyes grow heavy. Let's begin. Earth began about 4.56 billion years ago, when dust and ice around the young sun started merging into a single growing world. In the solar nebula, grains collided, stuck, and became pebbles that gathered into larger clumps. Gravity was the quiet matchmaker, turning swarms of debris into a few dominant bodies. Each collision added mass, but it also delivered heat, and the early Earth warmed with every strike. Short-lived radioactive elements added extra warmth, like embers mixed into the forming rock. Because the impacts were so frequent, the surface could not stay solid for long. Molten regions spread, and the planet began to round itself into a sphere. Even at this early stage, Earth's future depended on its ability to hold onto heavy elements and volatile gases alike. From the start, building a planet meant balancing loss to space with replenishment from within. A globe was taking shape, and time was already writing its first long sentences. Earth's interior separated into layers very early, as melting allowed heavy elements to sink and lighter materials to rise. In that global furnace, iron and nickel moved downward, while silicate rock gathered above as the mantle. This sorting happened because dense liquids fall through less dense ones, even when the motion is slow. The result was a metallic core that would later help power a magnetic field. Above it, the mantle became a thick, convecting shell that could transport heat toward the surface. Earth's size made the structure durable, with a radius of about 3,960 miles, around 6,370 kilometers. Heat could not escape instantly, so the interior kept working long after the surface cooled. Layering also concentrated certain elements, shaping what kinds of rocks could form later. With a core, mantle, and early crust, Earth gained an anatomy rather than a single uniform body. That anatomy would become the stage for oceans, air, and continents. Earth likely kindled a magnetic field once its core began to churn, turning motion into an invisible shield. Heat leaking outward drove currents in liquid metal, and moving conductors can generate magnetism. The young sun was more active than today, sending charged particles outward in frequent storms. Those particles can strip atmospheres over long spans, especially the lightest gases high above a planet. A magnetic field does not block sunlight, but it redirects many charged particles around Earth instead of through it. This protection reduced atmospheric loss and helped water remain part of the planet's story. The field itself could wax and wane as the core cooled and its flow patterns shifted. In the upper air, auroras would have danced where magnetism met the solar wind. Deep below, the core's stirring linked space weather to the planet's hidden heat engine. It was a force of guidance rather than force, helping Earth keep what it was trying to become. The moon formed very early, probably around 4.5 billion years ago, after a Mars-sized body struck the young Earth. The collision was immense, mixing rock and metal and flinging vaporized debris into orbit. That debris circled as a glowing ring, then gathered under gravity into one companion. With the moon close, Earth's sky gained a nearby partner that pulled on oceans and crust alike. The impact also changed Earth's rotation and tilt, setting the basic geometry of seasons. Heat from the event likely stirred the mantle, prolonging volcanism and reshaping the earliest crust. Because the Moon formed from Earth-like material, its composition became a clue to this shared origin. Over time, the Earth-Moon pair traded angular momentum, slowly widening the distance between them. The partnership made tides, stabilized tilt to some degree, and gave the planet a rhythmic tug. With a companion in orbit, Earth found a new kind of order amid early chaos. The newborn Moon raised powerful tides, and tides became a steady sculptor once water finally settled into oceans. When the Moon was closer, its pull was stronger, and Earth's rotation was faster. Tidal bulges did not sit directly beneath the Moon, because fast-spinning water lagged behind the line of pull. That misalignment created friction, and friction turns organized motion into heat. As energy leaked away, Earth's spin slowed, and the Moon's orbit expanded outward. This exchange is still happening, though far more gently than in deep time. Tides also stirred coastlines, mixing nutrients and sediments whenever land and sea finally met. Even on a mostly ocean-covered planet, the tidal rhythm influenced currents and the movement of water masses. In this way, the Moon became an engineer of shorelines long before complex life arrived. Its tug still beats in every bay and estuary, and the young planet learned to keep time. A global magma ocean likely covered much of early Earth, and cooling it was the first great test of the planet's patience. Heat escaped to space, but frequent impacts kept reheating and remelting wide regions. Radioactive elements in the mantle added long-lasting warmth, like slow coals beneath a molten crust. As cooling began, crystals formed, floated, sank, and remixed, constantly changing the melt's composition. Denser minerals tended to sink, while lighter ones could rise, creating early chemical layering. Any crust that formed was thin, cracked, and easily recycled back into the hot interior. Volcanoes and fissures reopened the surface, letting gases and lava renew the skin again and again. Yet each cycle of cooling allowed the surface to remain solid a little longer. With time, the planet's outer shell began to hold shape long enough to be transformed by water and air. Earth was learning to trade raw heat for a world with structure. Earth's first lasting atmosphere came largely from volcanic outgassing, as the interior released gases into the open sky. Volcanoes exhaled water vapor, carbon dioxide, nitrogen, sulfur compounds, and many trace gases. Without free oxygen, the air was chemically reducing, and sunlight drove intense photochemistry overhead. Carbon dioxide and water vapor trapped heat efficiently, helping prevent global freezing under a dimmer sun. Sulfur gases and aerosols could also cool the surface by reflecting sunlight, creating a constant tug of warming and cooling. The atmosphere was not a finished product, but a conversation between mantle, oceans, and space. Some gases escaped upward and were lost, while others dissolved into rain and seawater. Lightning and ultraviolet light broke molecules and stitched them back together in new combinations. In this early breath, Earth prepared the conditions that later allowed water to persist on the surface. It was a sky under construction, and its chemistry would shape every era that followed. The first oceans formed as Earth cooled enough for water vapor to condense and fall as rain, turning steam into seas. Once temperatures dropped, clouds thickened, and long downpours returned water from the sky to the ground. Basins filled, and water spread across dark basalt, dissolving minerals and carrying salts into the growing ocean. Some water likely arrived with hydrated minerals and icy bodies, but much came from Earth's own outgassing. As the ocean deepened, it became a massive heat reservoir that moderated temperature swings. Water also began the planet's habit of carving and depositing, even before recognizable continents existed. Chemical reactions between seawater and fresh crust altered both, creating new minerals and changing seawater's composition. Evaporation and condensation set up the earliest water cycle, with clouds as moving rivers in the sky. With oceans present, Earth gained a reflective surface that interacted with sunlight and climate. At last, the planet's face could mirror the heavens in liquid form. In Earth's first few 100 million years, impacts were common enough to repeatedly reshape the surface and influence the planet's volatile inventory. Leftover bodies still crossed Earth's path, and collisions were a frequent punctuation mark in early time. A large impact could vaporize rock, disturb oceans locally, and loft dust high into the atmosphere. That dust could dim sunlight for a while, nudging climate and chemistry in temporary directions. Yet impacts also delivered water and carbon-bearing materials, adding ingredients the young planet could keep. Each collision mixed crust and mantle, resetting parts of the surface like a rough edit of a draft world. Crater records from this era are mostly erased on Earth by later recycling, but the consequences remain. Some impacts may have helped the core and mantle continue differentiating by adding heat at key moments. Others fractured crust, opening pathways for volcanism and for seawater to react with fresh rock. Even destruction had a creative side, and Earth learned to grow through disturbance. Tiny crystals called zircons preserve some of the oldest direct evidence about early Earth, hinting that water and crust existed surprisingly early. Zircons are tough, able to survive later melting and erosion that destroys many other rocks. Some have been dated to more than 4 billion years old, reaching back toward the Hadean. Their isotopes and trace elements can record whether their parent melts interacted with liquid water. Many zircons suggest silica-rich melts, which often form when crust is reworked and becomes more continental in character. This implies that early Earth may have had patches of differentiated crust rather than only uniform basalt. Water helps drive such reworking by lowering melting temperatures and transporting elements. Because zircons are tiny time capsules, they let modern geology hear whispers from an otherwise vanished world. They do not show the whole planet, but they reveal that complexity began early. In those crystals, Earth's first experiments in making stable land are still quietly legible. Whether plate tectonics began early or later, Earth's hot interior ensured that the surface was never truly still. Today, plates move because the mantle convex, and early Earth had even more heat to lose. One possibility is an episodic regime, where the outer lid thickened, then failed, then reorganized in bursts. Another possibility is that subduction-like recycling started in fragments and gradually became widespread. Either way, deformation would have opened cracks, created volcanic arcs, and renewed oceanic crust repeatedly. Recycling matters because it transports water and carbon downward and returns them upward through volcanism. It also allows continents to grow by adding material and by reworking existing crust into lighter compositions. Even without modern-looking plate boundaries, the planet could still cool by moving its surface around. This motion tied the deep mantle to the sky, connecting rock physics to climate chemistry. In restless behavior, Earth found a way to shed heat without shutting down, Early oceans were low in oxygen and rich in dissolved iron, giving them a chemistry unlike modern seas. Without abundant oxygen in the air, iron could remain dissolved instead of rusting and settling out quickly. Hydrothermal vents added metals and reduced gases, feeding chemical gradients across the seafloor. Sunlight filtered through a hazier atmosphere, and the ocean's color would have been shaped by minerals and particles. As iron and silica cycled, sediments accumulated in layers, building a slow archive on the ocean floor. Some of those layers later became banded iron formations, rocks that record changing ocean chemistry through time. Because oxygen was scarce, many reactions favored different products than they do in modern seawater. The ocean was both a solvent and a reactor, dissolving new crust and precipitating minerals in return. These processes influenced how nutrients and carbon moved, long before complex ecosystems appeared. Earth's early sea was a world of metal, heat, and steady reaction. The faint young sun created a puzzle, because early sunlight was weaker even as evidence suggests liquid oceans existed on Earth. The sun brightens over its lifetime, so billions of years ago it delivered less energy to Earth's surface. On a modern atmospheric composition, that would likely freeze the ocean into a global shell of ice. Earth avoided that outcome by building a stronger greenhouse, using gases that trap heat efficiently. Carbon dioxide from volcanoes and methane from early processes could warm the surface despite lower sunlight. Clouds and aerosols complicated the balance, sometimes reflecting light away, sometimes insulating warmth below. When the planet cooled, weathering and biological or chemical sinks slowed, allowing greenhouse gases to accumulate. When the planet warmed, weathering sped up, drawing down carbon dioxide and easing temperatures back. These feedbacks acted like a planetary negotiation, keeping water liquid across long spans. Through that balancing act, the long experiment of a habitable ocean continued. Cratons, the oldest stable cores of continents, formed through repeated melting, intrusion, and thickening over immense time. Unlike dense oceanic crust, which is easily recycled, buoyant continental crust can persist at the surface for eons. In the Archean, higher internal heat encouraged frequent melting and vigorous reworking of early rocks. Basalt could be transformed through partial melting and differentiation into lighter, silica-rich compositions. Granite-like rocks accumulated, and thick keels of cool, rigid lithosphere began to root into the mantle. These keels made cratons mechanically strong, letting them resist being pulled back down into hotter depths. Small land masses likely rose and sank with changing buoyancy, and shorelines appeared, vanished, and reappeared. Rivers were modest at first, but even short flows could carry weathered minerals into nearby seas. Each surviving craton became a durable page in Earth's memory, preserving pieces of the earliest crust. From these scattered anchors, the future continents would slowly assemble their broader shapes. By about 4 to 3.6 billion years ago, in the early Archean, Earth likely had long-lived oceans and a crust that could persist for meaningful intervals. The interior was still hotter than today, and volcanism was widespread across the seafloor and islands. Yet the surface had cooled enough that water could cover much of the globe without constant global boiling. Oceanic crust formed at ridges, reacted with seawater, and became hydrated, storing water in minerals. When that crust sank or thickened, it could carry water downward, altering melting and feeding volcanism elsewhere. The ocean moderated climate by absorbing heat and releasing it slowly. smoothing extremes between day and night. Sediments began to gather more consistently, making the first long-lived seabed archives. Chemical cycles linked air and sea, with gases dissolving into water and minerals returning them to rock. Earth now behaved less like a transient magma sphere and more like a self-adjusting system. The early Archean was not calm, but it was coherent. Hydrothermal circulation on the seafloor became a crucial meeting place between rock and water on early Earth. Seawater seeped into cracks in hot crust, heated, reacted with minerals, and rose back out through vents. This carried dissolved metals into the ocean and altered seawater's chemistry in persistent ways. Hydrothermal systems also transported heat from the interior into the ocean, shaping local circulation. Where hot fluids met cold water, minerals precipitated, building chimneys and crusts like slow-growing stone gardens. Reactions between water and rock could produce hydrogen and other reduced compounds, changing the ocean's redox balance. Altered crust became denser or lighter depending on minerals formed, influencing how easily it could later be recycled. These systems effectively stitched the deep Earth to the ocean, exchanging matter in both directions. Even without continents, the seafloor itself hosted complex landscapes shaped by heat and chemistry. In those hidden currents, Earth learned to cool efficiently while enriching its seas. The carbon-silicate cycle began acting as a planetary thermostat, linking volcanoes, rain, rivers, and the chemistry of oceans. Volcanoes released carbon dioxide from the mantle into the air, strengthening the greenhouse and warming the surface. Rainwater absorbed some of that carbon dioxide, becoming slightly acidic and more able to weather rock. Weathering consumed carbon dioxide and carried dissolved ions to the ocean, where carbon could be locked into carbonate minerals. Burial of those minerals removed carbon from the atmosphere-ocean system for long intervals. Subduction, or deep burial, could later return carbon to the mantle, and volcanism would release it again. If Earth cooled too much, weathering slowed, allowing volcanic carbon dioxide to build up and warm the planet. If Earth warmed too much, weathering sped up, drawing down carbon dioxide and easing temperatures. This feedback did not prevent all extremes, but it gave the planet a stabilizing tendency. With that loop in place, oceans could stay liquid under a changing sun. Earth's atmosphere has always been in dialogue with space, and early on ultraviolet light and solar wind worked to erode and rearrange the upper air. High-energy sunlight can break molecules apart, creating fast atoms and ions that drift upward. Light gases, especially hydrogen, escape most easily, and their loss can slowly change a planet's chemistry. Repeated heating of the upper atmosphere can also swell it, making escape more likely during active solar periods. Earth's gravity helps retention, but gravity alone is not always enough when the young sun is fierce. Volcanic outgassing continually replenished gases, and oceans absorbed and released them in turn. The magnetic field reduced the direct stripping of ions by guiding many solar particles around the planet. In this way, Earth used both rebuilding and shielding to keep an atmosphere over billions of years. The result was a stable enough sky for water to persist and for climate feedbacks to operate. Between rock and open space, Earth kept its air because it continually rebuilt it. Earth's rotation slowed over time as tidal friction transferred energy from spin into the Moon's widening orbit. In the distant past, Earth spun faster and the Moon orbited closer, so tides were stronger and more frequent. Tidal bulges were tugged slightly ahead or behind the Moon, and that offset created friction in the oceans and crust. Friction converts organized motion into heat, and the lost energy must go somewhere, so the Moon gains orbital energy. Today, the Moon recedes by a few centimeters per year, a tiny pace that adds up over geologic time. Earlier, the same mechanism likely acted more strongly, shortening the interval between tides and lengthening the day more quickly. A changing day length affects winds, waves, and the rhythm of heating and cooling across the surface. It also changes how tides mix coastal waters once broad shorelines exist. Earth and Moon have been trading momentum ever since their violent beginning. Their shared history is written in every tide, and it is still being revised. By the later Archean, Earth had assembled the essential planetary systems that would guide the rest of its history: an active interior, a persistent ocean, and an atmosphere tied to rock by cycling. The mantle kept convecting, reshaping crust through volcanism and recycling, while gradually losing heat to space. The core's motion sustained magnetic shielding, reducing atmospheric erosion and helping preserve surface water. Oceans buffered temperature, carried sediments, and stored dissolved minerals that influenced later chemistry. Weathering and burial began linking air and rock in durable feedback loops, especially through carbon cycling. Stable cratons provided anchors of long-lived crust, allowing shorelines and basins to last longer between resets. The planet was still very different from today, with a low oxygen sky and iron-rich seas. Yet its main organs were working together, making Earth more than a collection of parts. From here, oxygen, ice, and supercontinents would each take their turn shaping the surface. For now, the young world had found its working order, and it held. Oxygenic photosynthesis began nudging Earth toward an oxygen-rich future during the late Archean, roughly 2.7 to 2.5 billion years ago, even though the open air still held little free oxygen. In warm, shallow seas, microbial mats learned to split water and release oxygen, turning sunlight into a new kind of chemistry. Most of that oxygen never reached the sky because it was quickly consumed by volcanic gases, fresh basalt, and abundant dissolved iron. The ocean acted like a vast chemical buffer, taking oxygen into reactions that left behind minerals instead of breathable air. Over time, those reactions gradually filled the planet's largest sinks, and the balance began to change. Even before the atmosphere responded, shorelines and seafloors were already being quietly remodeled. Earth was rehearsing a new identity in the language of oxidation. The stage was set long before the curtain rose. Banded iron formations preserved the fact that early oceans were iron-rich, and that rising oxygen forced iron to fall out of seawater as solid minerals. When oxygen produced in sunlit surface waters met deeper, iron-laden water, dissolved iron oxidized and precipitated, settling like rusting snow to the seafloor. Layer upon layer formed, often alternating iron-rich bands with silica-rich bands, as currents, seasons, and biological activity shifted over long spans. These deposits turned invisible reactions into rock archives that could endure for billions of years. Their existence implies an ocean that could hold vast dissolved metal without instantly rusting it away, a chemistry only possible with little oxygen in the air. As oxygen production grew, the iron supply in seawater was gradually stripped down. The bands marked the slow handover from a metal-rich sea to a more oxidized world. Many later mountains carry these stripes as a quiet signature. The Great Oxygenation Event, centered around about 2.4 billion years ago, in the Paleo-Proterozoic, marked the first sustained rise of oxygen in Earth's atmosphere. After ages of being consumed in the ocean and crust, oxygen began accumulating in the air because key sinks weakened and more reduced material became buried or sealed away. Ancient sulfur-bearing rocks reveal that an earlier weird sulfur fingerprint disappeared once oxygen crossed a critical threshold because atmospheric chemistry stopped allowing those old pathways. That change is a rare kind of evidence, not a fossil of a creature, but a fossil of air itself. With oxygen present, the sky became a more reactive place, and the oceans began to respond in new ways. Greenhouse balance shifted as methane became harder to keep, and sunlight began to work on a different mixture of gases. Earth's atmosphere had become an active actor, able to reshape climate and surface rock over immense time. Rising oxygen transformed the planet's chemistry by changing how carbon, sulfur, and iron could travel between air, ocean, and rock. In an oxygen-poor world, many gases linger longer, and sunlight favors reduced compounds in the upper atmosphere. As oxygen increased, new reaction pathways opened and older ones closed, like river channels reshaped by a changing floodplain. Sulfur compounds that once circulated freely began to oxidize and deposit differently, shifting the balance between volcanic release and sedimentary burial. Iron that had stayed dissolved in seawater increasingly rusted out, reorganizing nutrient availability and seafloor sediments. Carbon cycling also changed character because oxidation affects how organic matter is preserved versus recycled. The combined effect was not a single switch, but a cascade of linked adjustments across oceans, land, and air. Earth's surface chemistry became more complex, and that complexity began to store information in minerals. The planet was learning new rules and writing them into stone. The oxygen rise likely contributed to major Paleo-Proterozoic glaciations around 2.4 to 2.2 billion years ago by weakening methane's warming influence and pushing climate toward deeper cold. Methane is a powerful greenhouse gas, and in earlier air it could accumulate more easily. As oxygen became more common, methane was converted into carbon dioxide and water, and the net greenhouse effect may have dropped sharply. Once ice expanded, its bright surface reflected sunlight, reinforcing cooling in a strong feedback loop. Glacial deposits from this era appear in places that once lay at low latitudes, implying ice reached far beyond polar regions. Yet volcanism never stopped, and over long spans carbon dioxide could rebuild, warming the planet back toward liquid water. In some places, jumbled glacial debris became stone, preserving the chill. Earth's climate was proving it could swing widely when atmospheric chemistry changed. Ice was not merely weather, it was geology in motion. Oxygen's arrival expanded Earth's mineral palette because oxidizing conditions allow many new stable compounds to form at the surface. Before oxygen, metals tended to stay in reduced states, limiting which minerals could exist outside hot interiors. With oxygen, iron, manganese, copper, and others gained new oxidation states, creating new minerals and new colors in rocks. Sediments began to show widespread red staining from iron oxides, a clear signal that oxidation was no longer rare or local. Weathering also changed because oxygen let certain reactions proceed faster and in different directions, altering which elements are mobile in water. This reshaped the chemistry of rivers and coastal seas, and it changed what got locked away in sediments. Over time, the crust became a richer chemical workshop, able to build and preserve more varied compounds. Mineral diversity is a kind of planetary memory because it stores the history of conditions that allowed it. With oxygen, Earth's surface acquired a broader vocabulary for recording time. An ozone layer began forming once oxygen became sufficiently common, and that high-altitude shield changed how ultraviolet light reached Earth's surface. Ozone forms when ultraviolet radiation splits oxygen molecules and the fragments recombine into a 3-atom version that absorbs ultraviolet efficiently. Much of this protective layer sits in the stratosphere, roughly 20 miles, about 30 kilometers, above the ground today, filtering the harshest wavelengths. The result is not dimness but refinement, a shift in which photons can reach the sea surface and the land. Ozone also alters upper atmosphere chemistry by controlling how molecules break apart and recombine. With a stronger ozone screen, the surface environment becomes more stable against certain kinds of photochemical stress. This stability matters to the planet's chemistry because it changes the rates of reactions in air and surface waters. Earth's sky gained a new structure, like an invisible roof that shaped the light below. The atmosphere was becoming layered, purposeful, and enduring. As continents grew broader during the Proterozoic, weathering and sedimentation became stronger planetary forces, because more land meant more rock exposed to rain and rivers. Chemical weathering consumes carbon dioxide, so expanding continental area could tug the atmosphere toward cooler states over long spans. Rivers delivered dissolved ions and fine sediments to the ocean, feeding carbonate deposition and building thick sedimentary layers on continental shelves. Those layers became archives of sea level, chemistry, and climate, laid down grain by grain. More land also meant more shoreline, where ocean water meets fresh minerals and exchanges elements rapidly. Nutrients delivered to the sea can influence productivity, and productivity influences how much carbon is buried versus returned to the air. Even without focusing on life's details, the consequence is clear. The surface became more interactive, with tighter coupling between land, sea, and sky. Continents gave Earth more edges, and edges are where systems exchange power. The planet was growing a more intricate skin. Cooling of the mantle helped tectonics become more organized, allowing larger plates to persist and interact over longer timescales. When the mantle is hotter, rock is weaker, and convection can be more vigorous, sometimes favoring short-lived surface patterns. As Earth lost heat, the lithosphere could strengthen, making it easier for coherent plates to form and for subduction to operate steadily where conditions permitted. Subduction drags hydrated crust and carbon-bearing sediments downward, feeding arc volcanism and returning gases to the atmosphere. It also builds continents by adding material and by reworking existing crust into lighter compositions. The deeper the recycling, the more Earth's surface becomes connected to its interior, like a circulatory system linking skin to core. Plate boundaries concentrate earthquakes and volcanism, but over geologic time, they also concentrate change, creating new basins, ridges, and mountain belts. In this era, Earth's engine became more disciplined, not quieter. The planet was learning to cool without freezing its dynamism. The supercontinent Nuna, also known as Columbia, assembled roughly between 1.9 and 1.6 billion years ago, showing that continents had learned to merge into vast, long-lived configurations. Collisions welded cratons together, raising mountain belts that later eroded into immense sediment fans and broad plains. As land clustered, coastlines simplified, and interior regions grew farther from ocean moisture. strengthening dry climates and sharp seasonal contrasts. A place 1,600 miles, about 2,600 kilometers, from the sea can become dry even on a watery planet, because humid air loses its water before it reaches the center. Supercontinent assembly also changes ocean circulation by blocking pathways and redirecting currents, altering how heat moves around the globe. Mountain building increases weathering and can draw down carbon dioxide, while rifting later tends to reverse patterns by opening new seas. Nuna was not a single moment, but a long chapter of joining, pressing, and stabilizing. Earth was experimenting with continental scale, seeing what happens when land becomes a continent-spanning continent. The crust was learning to travel in crowds. When Nuna matured, the mountain belts from its collisions fed long erosion cycles that redistributed mass and altered sea level on regional scales. Thickened crust stands high, but over time it is worn down, and the sediments it sheds can fill basins and load continental margins. That loading bends the lithosphere, creating space for yet more sediment, a feedback between weight and subsidence that can persist for tens of millions of years. Sediment blankets also insulate the crust, changing how heat flows upward and how fluids circulate through rock. Weathering of uplifted regions continues consuming carbon dioxide, linking mountain height to atmospheric composition. Meanwhile, shallow seas creeping onto low continents create wide shelves where carbonates can accumulate, storing carbon in stone. The map of land and sea is never only geography. It is also chemistry and climate in motion. Nuna's interior and its margins were both active, just in different ways. One shaping winds and rivers, the other shaping seas and sediments. Earth was learning to smooth its own roughness without ever stopping. Nuna eventually began to fragment as rifts opened and stretched the continental crust, preparing the birth of new ocean basins. Rifting often starts where mantle heat rises, weakening the lithosphere from below and encouraging extension. Faults step downward, valleys subside, and magma injects into cracks, turning stress into new igneous rock. As the split widens, seawater floods the lowlands, creating long, narrow seas that can evolve into true oceans once seafloor spreading begins. Fresh oceanic crust forms at ridges, and hydrothermal circulation restarts the exchange of heat and elements between rock and water. New coastlines multiply, and with them new zones of weathering, sediment delivery, and chemical mixing. The breakup of a supercontinent is not merely a rearrangement of land, it is a rerouting of currents and winds that can shift climate patterns globally. Earth's crust was learning a repeating rhythm: gather, thicken, and then tear. In that rhythm, the planet ventilates itself, releasing heat and renewing its surface. Separation becomes another form of creation. During much of the mid-Proterozoic, Earth's atmosphere and oceans maintained relatively steady oxygen levels, creating a long interval of chemical stability from roughly 1.8 billion to 800 million years ago. This is often nicknamed the boring billion, yet the planet remained active in subtler ways that simply left fewer dramatic spikes in the record. Continents drifted, seas advanced and retreated, and sediments accumulated in great thicknesses along quiet margins. The deep ocean may have stayed partly oxygen poor, while surface waters held modest oxygen, limiting how far oxidation could penetrate. With fewer extremes, broad basins could persist, building layered sequences that now serve as long ledgers of sea level and chemistry. Mantle convection continued beneath, slowly cooling, still powering volcanism and recycling. The sun brightened gradually over this time, and Earth's thermostat adjusted by shifting greenhouse gases and weathering rates. The planet's stability was itself an achievement, a balanced stance held for an immense span. Quiet does not mean static, it means steady. A key planetary feature of the mid-Proterozoic may have been layered oxygen, with surface oceans mildly oxygenated, while deeper waters remained largely oxygen-poor. This arrangement can arise when oxygen production and vertical mixing are limited, while sinking organic matter consumes oxygen as it decays. In low oxygen deep water, metals like iron can stay dissolved, and sulfur can build up as sulfide, changing how nutrients and trace elements behave. When upwelling brings deep water toward the surface, sudden chemical shifts can occur, precipitating minerals and leaving distinctive signatures in sediments. This stratified ocean acts like a stacked atmosphere underwater, with each layer following different rules. Circulation patterns, temperature structure, and the shape of ocean basins influence how strongly layers stay separated or mix. Because oceans exchange gases with the air, layered oxygen also influences the atmosphere's long-term stability. The sea was not a uniform bath, but a structured system, and structure creates leverage for change. Earth's oceans were learning to keep secrets in their depths while still speaking to the sky above. Continental drift continued through the mid-Proterozoic at a pace of only a few inches per year. Yet that slow motion steadily rearranged climate belts. As plates carried land toward or away from the equator, the balance between tropical rainfall and high-latitude snowfall shifted across each craton. Paleomagnetic minerals in ancient rocks act like tiny frozen compasses, letting geologists infer where continents once sat relative to the spin axis. Latitude matters because sunlight is delivered unevenly, and the same land can be arid in one position and lushly weathered in another. Drift also changes which coastlines face prevailing winds and currents, influencing upwelling zones and the delivery of nutrients to surface waters. Over millions of years, these shifts alter sediment types, erosion rates, and the long-term drawdown of carbon dioxide. The continents move slowly enough to seem still on any human timescale, yet fast enough to redraw the planet repeatedly across geologic time. Earth's map was never fixed. It was a moving instrument. In motion, the crust conducted climate. Around 1.2 to 1 billion years ago, widespread mountain building signaled that continental collisions were again tightening the crust toward a new supercontinent. When plates converge, crust thickens and heats, and deep rocks transform under pressure into new mineral assemblages, recording the event like a memory in crystal form. Fluids released during metamorphism migrate and alter surrounding rock, and partial melting can produce granites that strengthen and diversify the continental interior. Uplifted mountains increase erosion and weathering, delivering new sediments to basins and influencing sea level regionally. Thickened roots can also make continents more buoyant and stable, helping them persist as long-lived blocks. These collisions do not just build peaks, they reorganize drainage networks, shift coastlines, and change where nutrients and carbon are transported. Even after mountains are worn down, their deep structural scars remain, guiding later rifting and later collisions. Earth's crust was tightening like a drawn bow, storing stress and potential in its geometry. The planet was preparing another vast gathering of land. In geology, compression is a form of anticipation. Rodinia assembled roughly between about 1.1 and and 0.9 billion years ago, and its great mass reorganized ocean circulation and climate by changing how water and air could travel. With continents clustered, some currents were blocked or diverted, reducing the ability of oceans to exchange heat between distant regions. Land heats and cools differently than sea, so concentrating land strengthened monsoons along some coasts while leaving interiors dry and temperature variable. Deep inland, far from maritime moisture, evaporation can outpace precipitation, promoting deserts and salty basins. The shape of coastlines also matters, because it controls where rivers deliver sediment and where shelves accumulate carbonates. By altering shelf area, Rodinia could influence how much carbon was locked into limestone versus returned to the atmosphere by volcanism. A supercontinent is not merely a landmass. It is a climate machine that changes the pathways of heat and water. Rodinia's assembly tightened the planet's circulation routes, like closing some doors and opening others. Earth was learning how continental architecture can steer air and sea. The surface became a design space built by collisions. A large supercontinent can help set the stage for global glaciation by accelerating carbon dioxide drawdown through tropical weathering and by amplifying ice reflectivity feedbacks. If Rodinia placed extensive land in warm, rainy latitudes, chemical weathering would have been vigorous, consuming carbon dioxide as rocks broke down and minerals formed. Over millions of years, that drawdown can weaken the greenhouse effect, cooling the planet enough for ice to advance into new regions. Once ice spreads, it reflects sunlight efficiently, reinforcing the cooling and making further ice growth easier. Meanwhile, changes in ocean circulation can redistribute heat less effectively, allowing cold to deepen in certain basins and along some coasts. The same tectonic processes that built Rodinia also built long mountain belts, and mountains enhance weathering by exposing fresh rock. Yet volcanism continues, slowly rebuilding atmospheric carbon dioxide, so the system is always a tug-of-war. Earth was approaching a sensitive edge, where small shifts could cascade into global change. The planet's thermostat does not click, it leans. Rodinia's geography encouraged the leaning. Rifting began to tear Rodinia apart between about 800 and 700 million years ago, opening new basins and exposing fresh basalt that could rapidly consume carbon dioxide through weathering. Extension fractures the crust into faulted blocks, and magma rises to fill gaps, building thick volcanic sequences along the rifts. As the rifts subside, seawater floods in, creating young seas with active margins and intense chemical exchange between water and rock. Fresh basalt is chemically eager. It reacts with water and carbon dioxide to form new minerals, pulling greenhouse gas out of the air over long spans. New continental margins also increase shelf area, changing where sediments accumulate and how ocean chemistry is buffered. Breakup multiplies coastlines, and coastlines are powerful reactors because waves, rain, and fresh rock meet there continuously. The opening of new oceans can reroute currents, changing how heat is delivered and removed at high latitudes. Rodinia's tearing was not a clean cut, but a long unraveling, and each new basin changed the planet's balance. Earth was renewing its edges again. In the seams of breakup, chemistry and climate found new leverage. By the late Neoproterozoic, just before the Cryogenian ice ages, Earth's climate system had become highly sensitive to feedbacks involving ice reflectivity, ocean circulation, and greenhouse gases. Subtle changes in Earth's orbit and axial tilt alter how sunlight is distributed, and those rhythms matter most when the planet is near a threshold. With continents broken into new configurations, coastlines shifted where moisture fell as snow versus rain, influencing how easily ice could accumulate and persist. Weathering of newly exposed volcanic rock could continue pulling carbon dioxide downward, while ongoing volcanism worked in the opposite direction, replenishing it. Ocean gateways were changing, and changing gateways change currents, and changing currents change where heat is stored. When ice begins to spread, its brightness increases the planet's reflectivity, and that can drive a rapid expansion if the system is already primed. The result is a world poised for dramatic transformation, not because the sun suddenly changed, but because Earth's own arrangement made feedback sharper. A threshold is an ordinary line until it is crossed. In deep time, Earth often approaches such lines slowly, and then responds quickly. The Cryogenian was waiting in the wings. Cryogenian glacial rocks reveal low-latitude ice because they were laid down on continents whose magnetic signatures place them near the equator. Some layers contain dropstones, large boulders released from drifting ice into fine mud, a clear sign of floating ice above liquid water. Other deposits show scratched clasts and jumbled tillites typical of grounded glaciers, dragging debris across land. Above many glacial beds sit cap carbonates, thick limestones that appear soon after deglaciation, suggesting warm seas rich in dissolved carbonate. Their carbon isotope patterns hint at a jolt in the carbon cycle, consistent with long greenhouse buildup followed by rapid weathering and rapid deposition. In some places, these layers drape over older landscapes like a fresh skin. The rock record cannot show every wave, but it preserves sequence and direction. Ice came, then stone from a revived sea arrived quickly. The strata hold that pivot with remarkable clarity. Even during near-global glaciation, the ocean beneath the ice likely continued circulating, powered by differences in salinity, temperature, and geothermal heat rising from the sea floor. When sea ice forms, it rejects salt, making nearby water denser so it sinks, and that sinking can drive slow, basin-wide motion, even without wind. Hydrothermal vents along mid-ocean ridges kept injecting heat and minerals, sustaining chemical gradients that shape seawater composition. Ice thickness is debated, but some models allow a few thousand feet, about a kilometer, in places, while other scenarios allow thinner tropical ice. Cracks and leads would have been rare but important, letting small amounts of gas exchange occur. Where ice was thinner, dim light could still reach the water and influence surface chemistry. Under the lid, the ocean remained an active machine rather than a stalled pool. Its slow currents carried heat, salt, and dissolved gases from basin to basin. Volcanism provided the long escape from cryogenian ice because carbon dioxide kept accumulating once weathering was suppressed by widespread ice cover. With land sealed under frozen surfaces, rain-driven reactions that normally consume CO2 slowed dramatically, while outgassing continued from arcs, hotspots, and mid-ocean ridges. Over millions of years, the greenhouse strengthened until melting began at lower latitudes, and then meltwater darkened the surface and absorbed more sunlight, accelerating retreat. As soon as open water appeared, evaporation returned and storms could rebuild the hydrologic cycle. Freshwater runoff surged across newly exposed rock, carrying ions and sediment into the sea. That runoff changed ocean density structure and helped restart vigorous surface mixing. Deglaciation may have been geologically abrupt, even if its preparation was slow. two-step pattern driven by feedbacks. CO2 concentrations were likely far higher than today because the usual sinks had been muted. The planet's thaw was an atmospheric decision expressed through ice. After a snowball episode, oceans and continents entered a period of intense chemical adjustment, and cap carbonates are one of its clearest signatures. High atmospheric carbon dioxide would have made rainwater more acidic, accelerating weathering of newly exposed rock and flushing calcium and bicarbonate into the sea. Warm post-glacial conditions and high alkalinity favor limestone precipitation, so carbonate layers could spread across shelves with surprising speed. As carbon became locked into stone, the greenhouse could relax, pulling the planet back from the brink of runaway warmth. Weathering also delivered nutrients in a pulse, altering productivity and the balance between oxygen and reduced compounds in coastal waters. In some successions, the first post-glacial sediments show abrupt chemical shifts, as if the ocean were resetting its bookkeeping after a long pause. The result was not a return to the old world, but a world retuned by ice and recovery. Earth cycles resumed, but with new starting conditions. The shelves became wide recording surfaces once more. By about 635 million years ago, the Ediacaran period opened with a warmer world and surface oceans that were more oxygenated than during much of earlier time. Oxygen levels were still below modern values, but they were high enough to expand oxidizing conditions across many shelves and shallow basins. That shift changed which minerals formed on land and seafloor, increasing iron oxides and altering how sulfur cycled through sediments. It also influenced how phosphorus, a key nutrient, was retained or released from mud, subtly steering coastal chemistry. Broad shelves became meeting grounds where seawater, sediment, and pore fluids exchanged elements continuously. The atmosphere gained a steadier ozone shield as oxygen persisted, changing the spectrum of ultraviolet light at the surface. These were not dramatic single moments, but durable trends. Rock chemistry could steer ocean chemistry, and ocean chemistry could steer air. The Ediacaran is a chapter where the planet's surface becomes more interconnected and more responsive. Late Neoproterozoic tectonics built mountains on a continental scale as collisions stitched landmasses into the growing framework of Gondwana during the Pan-African orogenies. When continents converge, crust thickens and uplifts, creating highlands that can stretch for thousands of miles, thousands of kilometers along a margin. Those uplands shed sediment for tens of millions of years, filling basins, building deltas, and widening continental shelves that reshaped coastlines. Uplift also exposes fresh rock terrain, enhancing weathering and gradually drawing down carbon dioxide, tightening climate's long knobs. The new geography redirected winds and currents, changing where moisture fell as rain or snow. Thickened crust can develop deep roots, helping some blocks remain buoyant and stable. Gondwana was not only a map change, it was a change in how Earth moved heat, water, and sediment. Continental assembly also alters ocean gateways, rerouting currents in ways that echo through climate. In this era, continents learned how to travel together for long intervals. Ediacaran sediments record a planet with restless sea levels and active continental margins, where repeated advances and retreats of shallow seas reshaped coastlines again and again. When sea level rises, shelves widen and carbonate production can expand. When it falls, rivers cut into exposed margins and later deliver pulses of sediment when the sea returns. These changes leave rhythmic layers that can be read like a ledger of shoreline motion, written in grain size, mineral type, and tiny chemical signals. Many basins preserve intervals rich in phosphorite, hinting that nutrient cycling and oxygenation were shifting with sea level and sediment supply. Shallow seas are responsive places. A small shift in depth changes waves, mixing, and how oxygen reaches the bottom. In rifted settings, new basins create room for water, while collision zones create sediment floods that fill that room. The coastline becomes a moving boundary between rock and sea. Through these oscillations, Earth tuned the chemistry of its shelves. Those balances fed directly into the Paleozoic seas that followed. The Cambrian period began about 541 million years ago, and one of its strongest planetary signatures is widespread flooding of continents by shallow seas. High sea level created broad, sunlit shelves where storms could stir sand and mud and where carbonate deposition often flourished. These basins became efficient factories for sediment, producing thick packages that now form cliffs, plateaus, and layered canyon walls in many regions. Seafloor mixing increased as burrowing churned the upper sediment, changing how oxygen and nutrients moved between water and mud. Even without dwelling on the organisms, the planet-level effect is clear. Sediments became more aerated and more chemically reactive. Shallow shelves also act as giant filters, trapping carbonates and clays before they reach the deep ocean. As tectonics shifted basin shapes, sea level rose and fell in long pulses. Each pulse moved shorelines across vast distances, redrawing chemical exchange zones. The Cambrian Sea was a broad, restless skin spread over the continents. In its layers, the planet stored a new kind of detail. Cambrian oceans built immense carbonate platforms that stored carbon in stone, forming limestones that in places reach hundreds of feet, tens to a few hundred meters, thick over long spans. Warm, shallow water favors calcium carbonate precipitation, especially where currents keep water clear, and shelves provide broad, gently sloping space. Layer upon layer accumulated, recording pulses of sea level change, shifts in sediment supply, and variations in ocean chemistry. Hard seafloor surfaces sometimes formed when sedimentation paused, cementing the seabed and creating firm horizons inside the stack. Storms could break and rework carbonate grains, moving them into bars and banks that later became stone ridges. Over millions of years, these platforms acted as major sinks for carbon, helping regulate the atmosphere by locking greenhouse carbon into rock. Where platforms drowned, deeper water shales and limestones recorded quieter, darker seas below them. The contrast between shallow and deep deposits makes sea level history visible. In this way, the Cambrian shelves became both factories and archives. Their thickness is time made tangible. During the Ordovician, roughly 485 to 444 million years ago, high sea levels and widespread shallow seas continued, but tectonics began raising new mountain belts that changed weathering and climate. Along the margin of what is now eastern North America, the tectonic orogeny uplifted terrain and delivered thick sediment loads to nearby basins, altering coastal circulation and seafloor conditions. Uplift exposes fresh rock, and fresh rock weathers quickly, consuming carbon dioxide and gradually weakening greenhouse warming. Volcanic arcs added ash and minerals, while newly formed basins trapped organic-rich muds that could lock carbon away. The layout of continents influenced currents, steering heat toward or away from polar regions and changing where sea ice could persist. Because shelves were so extensive, small sea level changes shifted thousands of miles of shoreline, thousands of kilometers, changing where carbonates formed and where mud accumulated. In this era, the planet's climate and its tectonics were tightly coupled through rock chemistry. Mountains did not merely rise, they altered the air above them. The Ordovician shows Earth's habit of translating uplift into global effect. The end Ordovician glaciation shows how a large landmass positioned over a pole can encourage ice growth and sea level fall, even on a generally ocean-rich planet. When Gondwana sat in high southern latitudes, snow could persist year to year, compacting into ice sheets that expanded outward. As ice stored water on land, global sea level dropped, shrinking shallow seas and exposing broad shelf areas to erosion. Shorelines migrated seaward, rivers cut deeper valleys, and new sediment packages were staged for delivery when the sea returned. Cold conditions also changed ocean circulation, because temperature and salinity patterns govern density and mixing. When the ice later waned, sea level rose again, reflooding shelves and transforming coastlines on a global scale. In effect, the planet briefly tightened its water budget, then loosened it again. The shelves responded everywhere. The rock record captures these swings as stacked layers of sudden shallows and sudden deeps. Earth's surface remembers ice not only in till, but in sea level architecture. Even brief glacial intervals can reshape the map. The Silurian period, about 444 to 419 million years ago, began with rising seas and a warmer rebound that reflooded shelves after late Ordovician ice waned. Shallow marine areas expanded again, and carbonate production resumed strongly in many basins, rebuilding platforms and reef complexes that influenced wave energy and sediment trapping. The return of higher sea level restored long coastal margins where seawater and fresh minerals meet, strengthening chemical exchange that helps regulate atmospheric carbon dioxide over long spans. Early vegetation on land, still small and patchy, began to influence weathering by stabilizing sediment and altering soil chemistry. Meanwhile, the arrangement of continents continued to steer currents, routing warm water into some basins and leaving others more isolated. Reef limestones could accumulate into buildups hundreds of feet, around 100 meters, thick, turning chemistry into durable architecture. These reefs also trap sediment and shape shoreline profiles, changing local circulation. The Silurian world shows how quickly Earth can shift from ice-dominated to sea-dominated landscapes when thresholds move. It is a reminder that recovery has its own momentum. Sea level, once rising, rewrites coastlines rapidly. As vegetation expanded across land through the Paleozoic, soils became a powerful planetary interface, turning bare rock into a chemically active layer that could reshape climate. Roots and microbes break minerals apart and produce acids that speed dissolution, increasing the flow of calcium and bicarbonate to rivers and then to the ocean. That river chemistry supports carbonate formation and long-term carbon storage in limestone, which can lower atmospheric CO2 over millions of years. Plants also trap sediment, reducing erosion spikes during storms and letting finer particles accumulate in floodplains. By creating soils, land ecosystems increase the land's ability to hold water, altering runoff timing and the delivery of nutrients to coastal seas. The ground surface became less like raw stone and more like a regulated membrane. Even small changes in soil coverage can shift the chemistry of rivers. Over time, this strengthens Earth's thermostat by making weathering more efficient and more widespread. The result is a planet where the atmosphere, rivers, and rocks are more tightly coupled. Biology acts as a catalyst rather than a separate layer. Soil is one of Earth's quiet inventions. It changes the conversation between rock and sky. The Devonian period, about 419 to 359 million years ago, reshaped Earth's surface as forests spread and river systems adopted more stable, sinuous forms across broad floodplains. Deep roots anchored banks and promoted thick soils, encouraging meandering channels and the development of wide deltas that built outward into shallow seas. Stabilized landscapes increased the depth and intensity of chemical weathering, pulling carbon dioxide from the atmosphere as minerals broke down and were carried away in solution. Sediment delivery changed character too, with more fine material stored on land rather than dumped abruptly offshore. This reshaped continental shelves by feeding longer-lasting sediment wedges and altering shoreline gradients. As forests expanded, organic carbon burial increased in some basins, leaving oxygen behind and influencing atmospheric composition. The planet's land surface became rougher and more structured, with canopies slowing rain and soils holding moisture. Rivers became more predictable sculptors, carving valleys while also building them with deposited layers. The Devonian is a chapter where the land learns new hydraulics. Those hydraulics, in turn, affect the sea. Earth's surface systems tightened their feedbacks again. Devonian ocean anoxic events reveal that Earth's oceans can slip into widespread low oxygen conditions when climate warmth, nutrient supply, and circulation combine in the wrong proportions. Warmer seawater holds less dissolved oxygen, and strong stratification can prevent oxygen-rich surface water from mixing into depth. If weathering and runoff increase nutrient delivery, surface productivity can rise, sending more organic matter downward where its decay consumes oxygen. The result can be broad anoxic zones that preserve organic-rich muds, later becoming black shales that lock carbon away for long spans. These events are recorded as dark layers with distinctive chemical signatures, including shifts in carbon isotopes and trace metals that respond to oxygen scarcity. Anoxia also changes sulfur chemistry, influencing how iron and other metals precipitate on the seafloor. Ocean basins are sensitive to gateway geometry, so tectonic rearrangements can worsen or relieve stagnation. In the Devonian, the seas were not always well ventilated, even as life flourished. The planet was experimenting with the limits of circulation. These experiments left thick, dark pages in the sedimentary archive. They also influenced climate by burying carbon efficiently. In this way, low oxygen at depth can connect back to air above. The Carboniferous period, roughly 359 to 299 million years ago, produced vast coal deposits and helped create an atmosphere with unusually high oxygen. In warm, low-lying tropical basins, plant material accumulated as peat faster than it decomposed, especially where waterlogged soils limited decay. Burial and pressure transformed that peat into coal, locking away carbon that had been drawn from the air and shifting the balance of the carbon-oxygen system. When carbon is buried as organic matter, oxygen can accumulate, and evidence suggests oxygen levels rose well above today's value during parts of this time. Meanwhile, large ice sheets grew and shrank on Gondwana, showing that despite tropical wetlands, Earth was in an icehouse state. Sea level rose and fell with the ice, repeatedly flooding and draining coastal lowlands where coal swamps formed. These oscillations built cyclothems, repeating sediment sequences that stack like layered breath in rock. The Carboniferous is therefore both a story of wet basins and of distant ice. It shows that climate can be regionally lush while globally cool. Carbon burial gave the atmosphere a new composition. That composition fed back into fire, weathering, and ecosystems. Earth's air became a different medium for the same sunlight. Late Paleozoic continental collisions built major mountain belts and pushed the continents toward the supercontinent Pangaea, reshaping winds, rainfall, and erosion at a global scale. The assembly of the Appalachians and related ranges formed long, rugged highlands that influenced atmospheric circulation, intercepting moist air and creating rain shadows downwind. Where mountains rose, weathering intensified, supplying sediment to adjacent basins and drawing down carbon dioxide over long intervals. Thick sediment loads bent the crust and created deep basins that collected more sediment still, a feedback between weight and subsidence. As land gathered into a single enormous mass, interiors drifted farther from ocean moisture, strengthening seasonal extremes and encouraging arid climates in many regions. The ocean, too, felt the change, as fewer seaways altered circulation routes and changed where deep waters formed. Monsoon systems intensified along some coasts because large continents heat strongly in summer and cool strongly in winter. Pangaea's growth was therefore a climate event as much as a tectonic event. The planet's geography began imposing stronger contrasts between coast and interior. Those contrasts shaped rivers, deserts, and shelf seas. In the late Paleozoic, the map itself became a climate engine. Earth was building a supercontinent with atmospheric consequences. The Permian period, about 299 to 252 million years ago, represents the height of Pangaea, when most land was joined and the oceans were reorganized into the vast Panthalassa and the smaller Tethys. With fewer seaways between continents, ocean circulation patterns shifted, affecting how heat and oxygen reached deeper waters and where upwelling brought nutrients to the surface. On land, the expanded interior lay far from maritime moisture, promoting deserts and strong seasonal temperature swings, recorded in dune sandstones and evaporite deposits. Coastal regions experienced powerful seasonal winds, including monsoon-like systems, driven by the continent's immense thermal contrast. Mountain belts continued to erode, feeding sediment far into basins and building broad continental plains. Sea level and shoreline position responded to tectonic subsidence and to remaining glacial influences in the south. The Permian is often read as an age of continental extremes, but it is also an age of reorganized oceans, where gateways and basins controlled ventilation. Chemistry followed circulation, and circulation followed geography. The planet's surface became more unified in land, yet more partitioned in climate zones. Pangaea's architecture shaped both air and sea. It set the stage for a dramatic boundary at its end. Near 252 million years ago, at the end of the Permian, the Siberian Traps eruptions flooded huge regions with basalt and released gases that shifted climate and ocean chemistry, leaving a sharp boundary in rocks worldwide. Lava piled into stacks that in places reached thousands of feet, around a kilometer thick, while carbon dioxide and sulfur compounds altered the atmosphere. Greenhouse warming would have heated the oceans, and warm water holds less oxygen, making it easier for deep waters to become poorly ventilated. If circulation weakened, anoxia could spread, changing sulfur chemistry and the availability of key trace metals. Acidification from added CO2 would also have stressed carbonate systems, altering how and where limestone could form. The boundary is marked by striking carbon isotope shifts, signaling a major disruption to the carbon cycle and its reservoirs. Even without lingering on biological consequences, the physical message is clear. Earth's surface environment changed rapidly relative to typical geologic pacing. Volcanism acted through the air, then through the sea, then into sediment. The Permian is a reminder that interior processes can rewrite surface conditions. It closes the Paleozoic with a powerful geochemical signature. The planet moved into the next era with altered oceans and altered skies. The Triassic period began about 252 million years ago, and Earth's surface entered a recovery landscape shaped by hot climates, shifting seas, and the slow repair of ocean circulation. After the Siberian traps, greenhouse gases likely kept temperatures elevated, and warm oceans struggled to hold oxygen, so deep water ventilation remained a central planetary challenge. On land, Pangaea's vast interior still promoted dryness, with large deserts and strong seasonal swings recorded in red beds and dune sandstones. Rivers carried sediment from worn mountain belts into broad basins, building layered plains that preserved footprints, mud cracks, and salt deposits. Life responded to these physical constraints by rebuilding ecosystems in step with the restabilizing carbon and oxygen cycles. Where coastlines returned, shallow seas once again became chemical reactors, exchanging carbonates and nutrients with the atmosphere. In this era, the planet's systems were finding a new balance point, and life was one of the tools that helped that balance hold. The Triassic is a chapter of rebuilding, where climate, chemistry, and living communities learn each other again. Through the Triassic, the carbon cycle tightened its feedbacks as weathering, burial, and volcanic release resumed a more regular exchange, with life acting as both driver and record. Plants on land increased soil formation, which accelerates chemical weathering and draws down carbon dioxide over long spans, even as volcanism continued returning CO2 from the interior. In the oceans, plankton and microbial communities helped move carbon from surface waters to sediments, a biological pump that influences how long carbon stays out of the air. When organic matter is buried, oxygen can accumulate. When it is oxidized, oxygen is consumed, so the balance of preservation versus decay matters to the atmosphere. Shallow shelves became important again, because they are places where carbonates form readily and where nutrient cycles can amplify productivity. The arrangement of continents still shaped currents and winds, guiding where upwelling fertilized seas and where water stagnated. The result was an Earth whose climate was not only a product of sunlight and rock, but also of living chemistry. Life did not replace geology, it partnered with it. In Triassic time, that partnership was regaining confidence. Rifting began to pull Pangaea apart during the late Triassic and early Jurassic, creating long lie valleys that later widened into oceans and changed Earth's circulation routes. Extension thinned the crust, faults stepped down into basins, and magma intruded as dikes and flows, turning tension into new rock. These rift basins trapped lakes and sediments, preserving thick sequences that record climate swings in their layers. As the split progressed, seawater invaded and new coastlines multiplied, increasing the area where weathering, sediment delivery, and carbonate formation could operate. New ocean corridors matter because they reroute currents that move heat around the globe, influencing how warm the poles become and how monsoons behave. Breakup also changes where nutrients enter the sea, because rivers and upwelling zones shift with geography. Life followed these new edges because edges are productive, mixed, and chemically dynamic. The planet was redrawing its boundaries again, and with each new boundary, climate and ecosystems gained a new stage. Pangaea's seams became tomorrow's shorelines. The end-Triassic boundary around 201 million years ago coincided with massive volcanism from the central Atlantic magmatic province, releasing gases that altered climate and ocean chemistry as the Atlantic began to open. Flood basalts and intrusions spread across what would become North America, South America, Africa, and Europe, injecting carbon dioxide that strengthened greenhouse warming. Rapid warming can intensify the water cycle, increasing rainfall and weathering, which in turn changes river chemistry and nutrient delivery to coastal seas. Sulfur emissions can produce aerosols that cool briefly, adding short-term volatility atop long-term warming. In the oceans, warming and stratification can reduce oxygen supply to depth, promoting anoxic conditions recorded in dark shales and chemical tracers. Carbon isotope shifts at this boundary suggest a major disturbance in how carbon moved between air, sea, and sediments. The physical environment changed fast enough to reorganize ecosystems, demonstrating again that Earth's interior can influence the surface through the atmosphere. This boundary is written not only in fossils, but in chemistry and rock type. It marks a moment when volcanism and a changing map combine to push Earth into a new Mesozoic mode. The story turns, and the planet keeps moving. The Jurassic period, about 201 to 145 million years ago, unfolded on a warm Earth with rising sea levels and a steadily widening Atlantic that began to rewire global ocean circulation. As continents separated, shallow seas flooded continental margins, creating broad shelves where carbonates accumulated and where nutrients cycled through coastal waters. Warm climates reduced polar ice, and with less ice, sea levels stayed high, letting marine sediments spread far across lowlands. Ocean currents adjusted to new gateways, and where circulation improved, deeper waters could carry more oxygen. Where basins became restricted, stagnation could persist. Reefs and carbonate platforms expanded in many regions, acting as massive geological engines built by living communities that turned seawater chemistry into limestone architecture. On land, climate belts shifted with drifting continents, changing where deserts formed and where humid forests could persist. The planet's surface was becoming more fragmented inland, yet more connected by shallow seas. This combination encouraged strong exchange between air and ocean through evaporation and storms. The Jurassic is a chapter where geography and life together build thick stone. In the layers of warm seas, Earth's chemistry becomes landscape. Jurassic carbonate platforms formed because warm, shallow, clear waters allow organisms and chemical processes to precipitate calcium carbonate efficiently, building reefs, banks, and broad limestone shelves. Where waves and currents kept sediment from smothering growing structures, carbonate production could outpace erosion and subsidence, stacking into thick sequences over millions of years. These platforms influence local circulation by shaping seafloor topography, creating lagoons, channels, and barriers that trap sediment and alter water exchange. They also act as carbon sinks, pulling dissolved inorganic carbon from seawater and storing it as limestone, which can influence atmospheric carbon dioxide over long spans through the carbon cycle. When sea level rose quickly or water became too deep, platforms could drown, switching from shallow limestones to deeper marls and shales. That transition is a readable signal of changing sea level, subsidence rates, and ocean chemistry. Reefs are therefore both living structures and geological recorders, converting biological activity into rock that can endure for hundreds of millions of years. In the Jurassic, these carbonate worlds were widespread and influential. They show how life can build geology at continental scale. Stone can be alive while it forms. Large igneous provinces continued to punctuate the Mesozoic, and they mattered because they could deliver enormous pulses of carbon dioxide that warmed climate and stressed ocean oxygenation. Basalt eruptions release not only lava, but also gases from magma and from heating of surrounding rocks, including carbon-rich sediments in some regions. A rapid increase in greenhouse gases warms the surface, and warmer oceans stratify more easily, which can reduce mixing and limit oxygen supply to deep water. Under low oxygen conditions, certain elements behave differently, leaving chemical fingerprints in sediments that later become black shales. These shales can lock away carbon, and over time that burial can help the climate recover by removing CO2 from active circulation. Volcanic aerosols can also cause short cooling episodes, making climate variability sharper during eruption intervals. Earth's surface responds through storms, erosion, and changes in nutrient runoff, linking air to rivers to sea. Life is part of the response because productivity and decay are central to oxygen balance in the water. In this way, volcanism can alter the planet through the carbon cycle and through ocean ventilation. The Mesozoic shows repeated episodes where interior heat briefly takes the steering wheel. Yet the system often finds a new equilibrium, written into rock layers as recovery sequences. The Cretaceous period, from about 145 to 66 million years ago, featured some of the highest sea levels of the Phanerozoic, with continents partly submerged under broad shallow seas. With little polar ice, water spread across lowlands, creating inland seaways that acted like warm, shallow corridors for currents and storms. These seas enhanced carbonate deposition and expanded habitats that built limestone and chalk, turning microscopic skeletal material into thick, pale layers. In the open oceans, plankton productivity helped drive the biological pump, sending organic matter to depth and influencing oxygen levels and carbon burial. The arrangement of continents continued to change, and new ocean basins altered circulation in ways that could either ventilate deep water or let it stagnate. At times, widespread ocean anoxic events occurred, when large regions of the deep sea became oxygen poor, preserving organic-rich sediments and shifting global carbon isotopes. These events reveal how warm climates, high nutrient supply, and restricted circulation can combine to change the ocean's chemistry on a planetary scale. The Cretaceous is therefore a warm water chapter, with strong coupling between life, carbonate sedimentation, and climate. The seas were high, and the planet wore water like a wide mantle. In that water, chemistry and biology wrote thick pages. Cretaceous chalk deposits, especially prominent in parts of Europe, record oceans rich in microscopic calcareous plankton, whose remains settled as a fine rain to the seafloor. Over immense time, those tiny shells accumulated into thick white layers that later hardened into chalk and limestone, sometimes reaching hundreds of feet, around 100 meters in thickness. Chalk forms best when the ocean is relatively clear of clay, meaning weathering inputs and circulation patterns favored carbonate sedimentation over muddy deposition. Because chalk is calcium carbonate, its accumulation locks carbon into rock, linking plankton ecology to long-term atmospheric composition through burial and later tectonic recycling. Chalk also records ocean chemistry, including shifts in carbonate saturation and changes in productivity that can be inferred from microfossils and isotopes. When sea level fell, chalk seas retreated and different sediments replaced them, making the chalk layers a marker of high stand conditions. These deposits show that small organisms can build large geology through patience and repetition. A storm can stir a shelf in a day, but chalk builds in quiet continuity. The Cretaceous oceans, in their calm intervals, created stone from countless tiny lives. That stone still shapes cliffs and coastlines today. Around 66 million years ago, the end Cretaceous impact marked a sharp turning point in Earth's surface conditions, as dust and aerosols altered sunlight, climate, and ocean chemistry over short timescales. The energy of the impact vaporized rock and lofted debris high into the atmosphere, where fine particles spread globally. Reduced sunlight would have cooled the surface temporarily, affecting evaporation, rainfall, and the productivity of surface oceans. Soot and sulfate aerosols could further dim light and change atmospheric chemistry, while acid rain from atmospheric reactions altered the chemistry of soils and shallow seas. At the same time, the Deccan Traps eruptions in India released additional gases, adding longer-term greenhouse effects to the recovery interval. The combined disturbances are recorded in a thin global layer rich in iridium and other impact markers, and in rapid shifts in carbon isotopes. In the oceans, altered circulation and reduced surface production affected oxygen levels at depth, reshaping sedimentation patterns. This boundary shows how quickly Earth's surface system can be perturbed by an external OODA, while still being guided by internal volcanism. The planet's climate machinery responded through air, then water, then rock deposition. The page turned, and the Cenozoic opened with a world reorganizing its energy balance. The planet remained the central character, even as the cast of life changed. The early Cenozoic, from 66 to about 34 million years ago, began on a generally warm Earth, with high carbon dioxide and oceans that carried heat far into high latitudes. Continents continued drifting toward more modern positions, changing ocean gateways and the shape of basins that steer currents. Warm conditions reduced permanent ice, so sea levels stayed relatively high, and shelves remained broad zones of exchange between land and sea. Chemical weathering continued to regulate CO2, while marine sediments recorded shifts in carbonate preservation as ocean chemistry adjusted. Life in the oceans, especially plankton, influenced how carbon moved to depth, shaping the balance between atmospheric CO2 and buried carbonates. On land, forests expanded into regions that later became cooler, leaving coal and sediment records of humid climates in places that are now temperate or even polar. The planet's thermostat was still set to warm, but it was beginning a long, gradual cooling trend, driven by tectonics, weathering, and evolving circulation. The Cenozoic is often described as a slide from greenhouse to icehouse. In its early chapter, the greenhouse still held. Earth was warm enough that palms and crocodilians once lived far north of their modern limits, a reminder that climate belts can migrate across time. The story was changing pace, not ending. The Paleocene to Eocene thermal maximum, about 56 million years ago, was a rapid warming event that shows how a sudden carbon pulse can reshape climate and ocean chemistry for tens of thousands of years. Evidence from carbon isotopes indicates a large injection of carbon into the atmosphere-ocean system, likely from a mix of sources such as methane hydrates, organic-rich sediments, and volcanic activity associated with North Atlantic rifting. Global temperatures rose several degrees, and warmer oceans became more acidic as CO2 dissolved into seawater, making it harder for carbonates to form and easier for existing carbonate sediments to dissolve. This change is recorded as a shoaling of the carbonate compensation depth, the level below which carbonate dissolves faster than it accumulates. On land, intensified rainfall and heat altered weathering and erosion, leaving distinct clay layers in some regions. The event did not last long by geologic standards, but its recovery required substantial carbon removal through weathering and burial. It is a clear example of Earth's sensitivity to carbon cycle disruptions and of the planet's ability to eventually restore balance through its slow feedbacks. Life responded, but the core mechanism is planetary: carbon, temperature, and ocean chemistry moving together. The PETM is a brief flare in the Cenozoic record. It shows how the atmosphere can change quickly and how the Earth system then spends time repairing itself. A fast shock meets a slow cure. After the PETM, the Eocene world stayed warm, but the direction of travel slowly turned toward cooling. Carbon dioxide remained higher than modern levels, and forests reached into high latitudes where winter darkness was long, yet the cold was gentle. The oceans carried heat poleward through broad gateways, and with little permanent ice, sea level stayed elevated, spreading shallow seas across continental margins. Over millions of years, the carbon cycle began to pull the reins tighter as weathering and burial slowly removed carbon from the fast-moving atmosphere-ocean system. Changes in ocean circulation helped because currents decide where heat gathers and where it escapes. In sediments, scientists read this long turn as a gradual shift in isotopes and fossil communities that prefer cooler waters. The Eocene teaches a quiet lesson. A planet can be warm for a long time, then cool not by a single switch, but by many small nudges adding together. One of the strongest reasons the Cenozoic cooled is that continents kept colliding, pushing fresh rock skyward where rain could work on it. India's northward journey ended in collision with Asia, and by roughly 55 to 40 million years ago, the Himalaya and Tibetan Plateau began rising into a vast highland. High mountains expose new minerals, and chemical weathering of those minerals consumes carbon dioxide, sending dissolved material to rivers and then to the sea. Over tens of millions of years, that drawdown can weaken greenhouse warming, especially when uplift is widespread and persistent. The growing plateau also changed atmospheric circulation by steering winds and shaping monsoon patterns, altering where rainfall falls and where erosion is strongest. Sediment carried from these mountains built huge fans and deltas, expanding the regions where carbon can be buried. This is geology that reaches into the sky. Uplift becomes chemistry, and chemistry becomes climate. While the Himalaya rose, other mountain belts also grew and changed how water and carbon moved across the surface. The Andes, building along the western edge of South America through much of the Cenozoic, redirected winds and rainfall, creating wet slopes and arid rain shadows that shaped regional deserts and river systems. Uplift increased erosion, and erosion fed sediment to the Pacific margin, altering shelf geometry and coastal upwelling zones. Those upwelling zones bring deep nutrients to the surface, influencing productivity and the burial of organic carbon in nearby basins. The Andes also helped reorganize drainage, at times steering water toward the Atlantic, and at other times trapping it in interior basins. Whenever drainage shifts, so does the delivery of minerals and nutrients that tune ocean chemistry. Mountains therefore act as valves for both water and carbon. In this way, long ridges of stone can influence the air and the sea far beyond their slopes. A major climate threshold arrived near 34 million years ago, at the Eocene to Oligocene transition, when Antarctica began to develop a large, persistent ice sheet. Evidence from oxygen isotopes in marine shells indicates a sharp shift toward colder conditions and more ice locked on land. Lower carbon dioxide likely helped, and so did changing ocean circulation as gateways around Antarctica opened and deepened. When ice grows on a continent, sea level falls because water is stored as land ice rather than ocean water. That drop can expose shelves, redirect rivers, and change where sediments and nutrients enter the sea. Ice also brightens the planet, reflecting sunlight and reinforcing cooling, especially once it becomes widespread. From this point onward, Earth had a major polar refrigerator that could expand or contract depending on greenhouse levels and orbital rhythms. The icehouse era had truly begun. Once Antarctica was glaciated, the Southern Ocean became a powerful organizer of global currents. As South America and Australia separated further from Antarctica, water could flow more freely around the continent, enabling a continuous circumpolar pathway. That pathway evolved into the Antarctic Circumpolar Current, a broad ring of moving water that helps isolate Antarctica from warmer subtropical seas. By limiting heat delivery to the Antarctic coast, the current supports the persistence of ice, and persistent ice strengthens the temperature contrast that powers strong winds over the Southern Ocean. Those winds drive upwelling that brings deep water to the surface, affecting how carbon dioxide is exchanged between ocean and air. In this way, a current is not only a conveyor of heat, but also a conveyor of chemistry. The Southern Ocean became both a barrier and a breathing place, shaping the climate of the whole planet through circulation and gas exchange. As Antarctic ice expanded and retreated during the Oligocene and Miocene, sea level rose and fell, repeatedly redrawing coastlines and sediment pathways. A drop of about 200 feet, around 60 meters, can expose enormous shelf areas, shifting river mouths outward and changing where deltas build. When sea level rises again, those exposed surfaces flood, and new shallow seas create fresh places for carbonate deposition and nutrient recycling. Glacial erosion also increases the delivery of fine rock flour to the ocean, changing water clarity and sometimes enhancing productivity in coastal zones. The loading and unloading of ice affects Earth's crust too, bending it under weight and letting it rebound when the ice melts. These processes leave stair-stepped shorelines and tilted lakebeds that preserve the memory of ancient water levels. In the icehouse world, the coastline becomes a moving ruler that measures the size of distant ice. The Miocene, from about 23 to 5.3 million years ago, opened with relatively warm conditions and then drifted into a cooler, more variable world. A notable warm interval, often called the Miocene climatic optimum, around 17 to 15 million years ago, saw reduced ice and expanded forests in many regions. After that, Antarctic ice strengthened again, and the global temperature trend resumed its slow decline. Carbon dioxide levels appear to have decreased over time, while mountain building and weathering continued to draw down greenhouse gases. Ocean circulation also evolved as seaways narrowed and continents moved, shifting where deep waters formed and how heat was transported. These changes influenced rainfall belts, which in turn controlled erosion and sediment delivery to the sea. Life responded to these physical shifts by reorganizing habitats, and those reorganizations fed back into carbon storage in soils and sediments. The Miocene shows a planet that can still be warm in an icehouse era, but only within the constraints set by currents and carbon. As grasslands expanded through parts of the Miocene, they altered Earth's surface in ways that mattered to climate and erosion. Open landscapes reflect sunlight differently than dense forests, and their root systems create soils with distinct structures and carbon storage patterns. In many regions, grasses encourage frequent small-scale fires that recycle nutrients rapidly, influencing how much organic carbon is buried versus returned to the air. With fewer trees, wind can lift more dust from dry surfaces, and dust can cool climate slightly by scattering sunlight, while also fertilizing the ocean with iron and other micronutrients. Fertilized oceans can increase biological carbon uptake, linking land aridity to marine carbon burial. Grasslands also support different styles of runoff, with intense storms moving water quickly across the surface and carrying sediment into rivers. Over long spans, these shifts can reshape floodplains and deltas. Here, vegetation is not scenery. It is a force that changes the chemistry and reflectivity of the planet's skin. Mountain uplift also reshaped rainfall patterns by guiding winds and concentrating storms, which in turn influenced weathering and the carbon cycle. The rise of the Himalaya and Tibetan Plateau strengthened monsoon circulation by creating a strong summer heating contrast and a high barrier that redirects airflow. Heavy seasonal rains enhance chemical weathering and carry vast sediment loads to rivers and deltas, building thick deposits that store carbonates and organic matter. Sediment delivery can also change coastal ecosystems by altering water clarity and the nutrient levels, which affects how carbon is cycled in shelf seas. Meanwhile, uplift in other regions, such as the East African highlands and parts of Western North America, modified regional rain shadows and encouraged the growth of deserts in some basins. Deserts supply dust, and dust influences both sunlight and ocean fertility. In this way, topography becomes climate, climate becomes erosion, and erosion becomes long-term carbon balance. Ocean gateways kept changing during the Miocene, and each change acted like a valve that could redirect currents and reshape climate. The gradual closure of the seaway between the ancient Mediterranean region and the Indian Ocean, and later restrictions near the Middle East, altered salt and heat exchange between basins. The Indonesian region also evolved as Australia moved northward, affecting the flow of warm water between the Pacific and Indian Oceans. When currents are rerouted, rainfall patterns often shift because warm water fuels evaporation and storms. Rerouting also changes where nutrients are delivered by upwelling, influencing marine productivity and the burial of carbon in sediments. Some basins became more isolated, making them more sensitive to oxygen loss at depth, while other regions became better ventilated. Even small changes in seafloor depth can matter, because shallow sills can block deep water exchange. Geography is a set of doors, and the ocean's circulation is the traffic that decides climate. A particularly influential gateway change occurred when the Isthmus of Panama rose and narrowed the connection between the Pacific and Atlantic, a process largely completed between about 4.5 and 3 million years ago. By restricting tropical water exchange, the Atlantic could become saltier, which favors dense water formation in the north and can strengthen circulation that carries heat poleward. Stronger northward heat transport also increases evaporation and snowfall at high latitudes, helping ice sheets grow when summer sunlight is weak. In the Pacific, altered circulation changed upwelling patterns and the distribution of nutrients, subtly reshaping marine productivity and carbon burial. On land, the new isthmus redirected rainfall by steering winds and concentrating storms on some coasts while drying others. A narrow land bridge, only about 50 miles, roughly 80 kilometers, across at its tightest modern span, ended an oceanic shortcut and left the climate system with a new set of routes and balances to explore. The Pliocene, from about 5.3 to 2.58 million years ago, was generally warmer than the coldest times that followed, yet it steadily trended toward a more ice-friendly world. CO2 levels were often similar to or modestly higher than pre-industrial values, and sea level stood higher at times because less water was locked in large ice sheets. Some estimates place parts of Pliocene sea level tens of feet, several to a few tens of meters above modern, enough to flood many coastal plains. Warmth was not uniform, because ocean currents still created strong regional patterns, but polar regions were often notably milder. As cooling progressed, Arctic sea ice and mountain glaciers became more persistent, and the background state of the planet shifted. This matters because once ice is present, orbital cycles can amplify it dramatically. The Pliocene is therefore a bridge, still warm enough to resemble earlier greenhouse moods in places, yet close enough to an ice threshold that small changes could tip the balance. Long before large ice sheets dominated, Earth's orbit and tilt were already quietly modulating sunlight, and those cycles become most visible when climate is near an ice threshold. Changes in eccentricity, tilt, and precession alter where and when solar energy arrives, especially in high-latitude summers that determine whether winter snow melts away. When summers are cool, snow can persist, brightening the surface and encouraging more cooling through reflectivity. Over time, small orbital nudges can be amplified by feedbacks involving ice, ocean circulation, and greenhouse gases. The key is that ice responds to summer sunlight more than to annual averages, because a cool summer preserves snow that would otherwise vanish. Sediments and ice cores record these rhythms as repeating patterns in isotopes, dust, and trapped gases. The cycles are not metronomes, but they provide pacing, and pacing matters when the system is ready to move. In the late Cenozoic, orbital geometry became a steady drummer behind the icehouse beat. The Quaternary period began about 2.58 million years ago, and it is defined by repeated glacial and interglacial cycles that reshape sea level and landscapes worldwide. During major glacials, ice sheets spread across North America and Eurasia, storing vast amounts of water on land and lowering global sea level by roughly 400 feet, about 120 meters at peak times. Exposed continental shelves became broad plains, and rivers extended their courses to distant shorelines. When ice melted, sea level rose again, drowning valleys and rebuilding coasts in new positions. These cycles also changed the atmosphere, because cold oceans and changing biology influenced how much carbon dioxide remained in the air. Ice ages tend to coincide with lower CO2 and warmer intervals with higher CO2, revealing a tight coupling between temperature and greenhouse gases. Winds strengthened in many regions during glacials, carrying more dust that affected sunlight and ocean fertilization. The Quaternary is Earth's recent chapter of large, repeated swings, written into moraines, loess, and submerged shorelines. Glaciers are powerful sculptors because ice can flow like a slow, heavy river, grinding rock and carrying debris over great distances. Where ice sheets advanced, they planed bedrock, carved basins, and left behind streamlined hills that reveal the direction of flow. Thick ice can be a mile, around 1.5 kilometers, deep in places, and that weight depresses the crust, pushing land downward under the load. When the ice retreats, the crust rebounds, lifting coastlines and tilting lake shores over thousands of years. Glaciers also generate fine rock flour, a powder that turns meltwater cloudy and can fertilize downstream ecosystems once it reaches rivers and seas. As meltwater pulses into the ocean, it can alter salinity and influence circulation patterns that redistribute heat. In this way, ice is not only carving the land, it is adjusting the plumbing of the ocean. The Quaternary landscape is, in many regions, a direct product of this moving, grinding, and rebounding machinery. Glacial deposits and landforms act like signatures of vanished ice, revealing where ice stood and how it moved. Moraines mark former ice margins as ridges of debris pushed or dropped at the edge of a glacier. Outwash plains form where meltwater spreads gravel and sand in braided channels, building broad, gently sloping fans. Drumlins and fluted surfaces show streamlined shapes molded beneath flowing ice, pointing like arrows in the direction of movement. In many areas, glaciers dammed rivers and created temporary lakes that later drained, leaving flat lake beds and sudden spillway channels. These features can stretch for tens to hundreds of miles, tens to hundreds of kilometers, and they often dictate modern drainage patterns. Even the distribution of soils reflects glacial history, because ice mixes and redistributes sediments of different textures. Where bedrock is scraped clean, thin soils and exposed stone dominate. Where till is thick, rich agricultural soils often form later. Ice leaves a map of its own making. Interglacials, the warmer intervals between major ice advances, offered Earth a different face. Higher seas, expanded forests, and reorganized currents. The last interglacial, around 125,000 years ago, is one example of a time when temperatures were modestly warmer in many regions, and sea level stood several feet to perhaps tens of feet, a few to several meters, above today's level. Warmer oceans expand slightly and help melt land ice, while changes in sunlight distribution can favor strong summer warmth in the far north. Higher seas flood coastal plains, shift estuaries inland, and change where sediments settle, turning river mouths into sheltered bays. Coral terraces, beach ridges, and marine fossils now stranded above modern shorelines preserve these past waterlines with surprising precision. Interglacials also reveal how quickly vegetation belts can migrate and how slowly the largest ice sheets answer back. They are rehearsals for change written in sand, limestone, and the memory of ice. The last glacial maximum, about 21,000 years ago, represents the peak of the most recent major ice expansion, when ice sheets reached their broadest extent and sea level was near its lowest. The Laurentide ice sheet covered much of North America, and Scandinavian ice spread across northern Europe, while mountain glaciers thickened in many ranges. In places, the ice was more than 10,000 feet, about 3 kilometers, thick, pressing the crust downward under its weight. With so much water stored as ice, coastlines shifted outward, and land bridges appeared where seas are now, changing the shape of continents. Atmospheric carbon dioxide fell to roughly 180 parts per million, reinforcing the cold. Dust was more common in the air, and winds carried it across oceans and onto ice, darkening some surfaces and feeding fertile loess on exposed plains. The hydrologic cycle slowed, and deserts expanded in many subtropical belts. Sea ice reached farther, and storm tracks shifted southward. Deglaciation began as sunlight patterns and greenhouse levels shifted, and melting ice set off feedbacks that transformed coastlines and rivers. As ice margins retreated, meltwater pooled into vast temporary lakes and then spilled through outlets, cutting channels and delivering pulses of fresh water to the oceans. Fresh water can disrupt ocean circulation by changing surface salinity, which influences density in the sinking that helps power deep currents. Rising seas drowned river valleys into estuaries, rebuilt deltas in new positions, and shifted shorelines inland by miles, kilometers, in many lowlands. Isostatic rebound lifted some formerly glaciated coasts, even as global sea level rose, creating stair-step beaches and tilted lake shores that still climb gently today. As vegetation returned, soil stabilized and dust loads declined, changing how sunlight was absorbed and how nutrients traveled. The end of an ice age is therefore not only warming, it is a sweeping rewiring of water, rock, and air. By about 11,700 years ago, the Holocene began, and the planet entered a comparatively stable warm interval that allowed coastlines, rivers, and soils to settle into long-lasting patterns. Ice retreated to high mountains and polar regions, sea level rose toward its modern position, and many continental shelves became submerged again. Ocean circulation regained a structure similar to today's, with strong exchanges of heat between tropics and higher latitudes, even as regional climates continued to vary. Lakes and wetlands spread in some regions, deserts shifted in others, and forests migrated as rainfall belts wandered. Over thousands of years, reefs rebuilt and deltas advanced, leaving layered records of changing sea level. In the air, carbon dioxide and methane remained low compared with earlier greenhouse epochs, and the planet's seasons settled into a familiar rhythm. Earth was ready for a new kind of surface disturbance, one that would arrive very late in the timeline, but it would still have to work within the rules of rock, water, and sky. The Younger Dryas, about 12,900 to 11,700 years ago, was a sudden return to cold that shows how abruptly Earth's climate can pivot. As the last great ice sheets melted, fresh water likely spilled into the North Atlantic and lightened the surface ocean. When water is less salty, it is less dense, and it sinks less readily, weakening the deep circulation that helps ferry warmth northward. With that conveyor reduced, sea ice spread, winds shifted, and temperatures fell across wide regions. Dust became more common in many records as landscapes dried and winds strengthened. For roughly 12 centuries the chill persisted. Then the shift reversed. Ice cores and lake sediments show not only the downturn, but also its sharp ending, as temperatures rose again in a matter of decades. The episode reminds us that oceans can act like a switchboard, routing heat and reshaping the sky. When the conveyor recovered, the planet stepped into the Holocene with a steadier rhythm. Holocene sea level rose rapidly after the last ice age and then slowed, turning a racing shoreline into a steadier one. From roughly 15,000 to 7,000 years ago, melting land ice raised global sea level by about 400 feet, around 120 meters, flooding continental shelves and transforming river valleys into estuaries. As the biggest ice reservoirs dwindled, the rate eased and coastlines lingered long enough for beaches, dunes, and tidal flats to organize themselves. Barrier islands could migrate and stabilize, and coral reefs could build upward without constantly being overtaken by rising water. Continental shelves became broad nurseries where waves, currents, and sediment could craft long sand ridges and mudplains, where rebound lifted some coasts and rising seas lifted others. Shorelines formed stairsteps that still mark ancient waterlines. By the mid-Holocene, the ocean was no longer sprinting across the map, and that slower pace let the modern coastline begin to take shape. The Holocene climatic optimum, roughly 9,000 to 5,000 years ago, was a time when many regions were slightly warmer or wetter than later millennia, shaped largely by orbital geometry. Early Holocene summers in the Northern Hemisphere received extra sunlight, strengthening seasonal heating and intensifying some monsoon systems. Lakes expanded in parts of Africa and Asia, and tree lines shifted poleward in several high-latitude regions. Warmer summers also influenced mountain glaciers, shrinking ice in some ranges while increasing meltwater that fed rivers and wetlands. In the oceans, changing winds and freshwater inputs adjusted surface mixing, subtly steering productivity and carbon burial. The event was not uniform. Some places dried even as others grew greener, because circulation moves moisture unevenly. Yet the overall message is consistent in many archives, from pollen to shoreline deposits. In this interval, Earth's seasons carried a slightly different emphasis, and landscapes responded with slow, measurable changes. It was warmth written in geography. The African humid period, strongest between about 11,000 and 5,000 years ago, turned parts of today's Sahara into a landscape of grasslands, rivers, and lakes. Enhanced summer sunlight over the Northern Hemisphere strengthened the West African monsoon and pulled moist air far inland. Vegetation then darkened the surface and anchored soils, increasing heat absorption and helping sustain rainfall in a feedback between plants and winds. Ancient lake beds preserve shells, fish remains, and shoreline ridges that trace former water levels across basins now filled with sand. When lakes expanded, evaporation recycled moisture locally, further feeding storms. As orbital forcing eased, rainfall belts retreated, and drying accelerated as bare ground reflected more light and held less moisture. Dust export increased, and that dust traveled over the Atlantic, fertilizing distant ocean waters with iron. The Sahara's green interval shows how climate, vegetation, and atmospheric transport can temporarily rewrite an entire region. The rocks remember the rain. The African humid period ended as orbital-driven sunlight weakened the West African monsoon, and the Sahara dried again. As Northern Hemisphere summers received less extra energy, the rain belt retreated southward, and lakes that once spread across basins began to shrink. Vegetation thinned, exposing brighter ground that reflected more sunlight and reinforced the drying. With fewer plants to hold moisture and soil, winds lifted more dust into the atmosphere. Ancient shorelines became ridges in the sand, and former river courses turned into quiet valleys that only rare storms revisit. That dust did not stay local. It traveled and changed the planet's radiative balance by scattering sunlight and seeding clouds. At the surface, salts concentrated where water evaporated, leaving mineral crusts that record the retreat of wetlands. Life adjusted by shifting toward drought-tolerant communities that could endure long intervals without steady rain. The change shows how a small orbital nudge can reorganize vegetation, wind, and water across a whole continent. Earth, even in the Holocene, continued to rewrite its landscapes through the geometry of sunlight. Holocene dust became a planetary traveler, crossing oceans and linking drylands to marine chemistry. Fine particles lifted from deserts can ride high winds for thousands of miles, several thousand kilometers, before settling. When dust lands on the ocean, micronutrients such as iron can stimulate surface plankton that draw carbon from seawater as they grow. Some of that carbon sinks as organic debris, strengthening the biological pump that influences atmospheric carbon dioxide over long spans. Dust also dims or brightens skies depending on particle size and altitude, subtly shifting how much solar energy reaches the sea surface. In coastal zones, dust can mix with riverborne minerals, enriching sediments that later harden into layered deposits. Over time, the exchange becomes a loop. Arid regions export dust, oceans respond biologically, and the carbon cycle adjusts its balance. The planet treats each grain as a messenger, carrying the story of a dry wind into a distant water column. In that way, the Sahara's breath can help feed a bloom far out at sea. Holocene sea level rise slowed enough by about 7,000 years ago that coastlines could stabilize and build lasting shore structures. When rapid meltwater pulses eased, beaches, dunes, and tidal flats lingered in place long enough to develop layered architecture. Barrier islands could migrate gradually rather than being drowned outright, and estuaries matured into mixing zones where fresh and salt water trade heat and nutrients. Salt marshes and mangroves expanded along many warm coasts, trapping sediment and storing carbon in waterlogged soils. Wave energy sculpted sand into long ridges, while quiet bays collected mud that records storms and river floods as thin laminations. As shoreline steadied, coral reefs and seagrass meadows found stable depths, turning sunlight into carbonate and organic storage. The coast became a wide interface, neither fully land nor fully sea, where chemistry moves quickly compared with the deep ocean. This slower sea level chapter allowed the modern coastal template to emerge, with its deltas, lagoons, and shelves writing time in sediments. Coral reefs became major Holocene builders by turning warm, shallow seawater chemistry into limestone frameworks. Reef organisms precipitate calcium carbonate, and as they grow and die, their skeletons pile into rigid structures that can withstand waves. In clear tropical water, reefs can accrete a few millimeters per year, a few tenths of an inch, enough to keep pace with slow sea level change. Their growth depends on light, temperature, and carbonate saturation. So shifts in ocean acidity and circulation leave signatures in reef layers. Reefs also reshape local currents by creating barriers and channels, which trap sand and calm lagoons behind the crest. Those sheltered waters nurture seagrasses and microbial mats that further alter sediment and nutrient cycling. During storms, broken coral fragments become beach sands, turning living architecture into movable grains that later cement into rock. Over centuries, reefs act as both shoreline guardians and carbon vaults, storing marine carbon in stone while guiding the flow of coastal water. Holocene river deltas expanded, where sediment supply and relative sea level allowed rivers to build outward into the sea. A delta forms when a river slows at its mouth and drops its load of sand, silt, and clay, creating branching channels and wide wetlands. Deltas are sensitive to the balance between incoming sediment and removal by waves, tides, and subsidence. Many deltas rise only a few feet, a meter or two, above sea level, making them responsive to small shifts in water level and storm energy. As channels jump and split, they paint the coastline with new lobes, then abandon them, leaving peat, mud, and sand in layered mosaics. Nutrients carried by rivers feed plankton blooms near the mouth, tying inland weathering to coastal productivity. Organic matter buried in delta wetlands can store carbon for long intervals, while the river continually delivers fresh minerals for further reactions. Each delta is a meeting place where mountains, rainfall, and the ocean negotiate a new shoreline. Holocene soils deepened and diversified as vegetation, microbes, and climate transformed rock fragments into structured ground. Weathering breaks minerals apart, but living roots and microbial acids accelerate the process and create clays that hold water. Organic matter from leaves and roots becomes humus, darkening soil and increasing its capacity to store nutrients and moisture. Different climates produce distinct soil profiles, from thin, stony layers in cold or dry regions to thick, deeply leached soils in warm, wet belts. Soils regulate runoff by absorbing rain, releasing it slowly to streams, and reducing the sharp pulses that bare rock would send downslope. They also store carbon in both plant fragments and mineral-bound forms, linking landscape health to atmospheric composition over time. Insects, fungi, and bacteria act as quiet engineers, mixing particles and building pores that let air and water circulate. By the Holocene, Earth's land surface had become a living membrane, turning sunlight-driven growth into chemistry that reshapes rock itself. Holocene peatlands grew as waterlogged landscapes accumulated plant material faster than it could decay, storing immense amounts of carbon. In saturated conditions, oxygen penetrates poorly, so dead vegetation builds into peat, rather than returning quickly to carbon dioxide. Over centuries, peat layers can reach many feet, several meters, thick, especially in cool northern bogs and in tropical wetlands. Peatlands also influence methane, because microbes in oxygen-poor water can produce it as they digest organic matter. Seasonal water table shifts decide how much methane escapes versus how much is consumed by other microbes near the surface. These wetlands cool and moisten local air through evaporation, and they soften floods by holding water like a sponge. When peat is buried and preserved, it becomes a long-term archive of pollen, dust, and ash, recording climate swings as subtle layers. Peat shows how life can lock atmospheric carbon into the ground, turning slow growth into a geological reservoir. Holocene forests and grasslands shaped climate locally by altering how the surface absorbs sunlight and exchanges water with the air. Dark canopies absorb more solar energy than bare ground or snow, yet they also cool the air through evaporation from leaves. In humid regions, forests recycle moisture and help feed clouds and rainfall downwind, creating feedback between vegetation and precipitation. In drier zones, grasses reflect more light and allow more wind to reach the ground, increasing dust and changing surface roughness. Root systems change infiltration, so the same storm can produce a gentle seep in one biome and a fast flood in another. Vegetation also influences snow cover by shading it or by trapping drifting snow, affecting winter insulation of the soil. Over seasons, plant communities act like adjustable valves on energy and water, shaping near-surface temperatures without moving a single mountain. In the Holocene, the living cover became one of Earth's most responsive climate tools, translating rainfall patterns into landscape-scale physics. El Niño and La Niña became familiar Holocene rhythms because the tropical Pacific is a powerful engine for exchanging heat between ocean and atmosphere. In an El Niño state, warm surface water spreads eastward, shifting rainfall patterns across the Pacific and sending atmospheric ripples into distant regions. In a La Niña state, stronger trade winds pile warm water westward and enhance upwelling of cool, nutrient-rich water in the east. These swings influence marine productivity because upwelling brings nitrates and phosphates that feed plankton near the sunlit surface. Changes in cloud cover then alter how much sunlight enters the ocean, closing a feedback loop between sea temperature and the sky above. Sediments and corals can record these variations as chemical bands, turning climate noise into readable patterns. The oscillation is not perfectly regular, yet it is persistent enough to shape drought and flood tendencies over years. In this way, one ocean basin acts as a planetary metronome, tapping out pulses of heat that the atmosphere carries worldwide. The Atlantic overturning circulation remained a key Holocene conveyor because it carries warm surface water northward and returns cold deep water southward. Where surface water becomes dense enough, it sinks and pulls more water behind it, like a slow pump that spans basins. Density depends on temperature and salinity, so fresh water from rainfall, rivers, and melting ice can influence the pump's strength. When overturning is strong, the North Atlantic tends to be milder, and sea ice retreats, changing how much sunlight the ocean absorbs. When overturning weakens, heat transport shifts and weather patterns can reorganize across the surrounding continents and seas. Deep waters also store carbon and nutrients, so the rate of sinking helps set how quickly the ocean can sequester carbon from the surface. Over centuries, this circulation writes its signature into sediments through changes in grain size and chemical traces. In the Holocene, the Atlantic acted as a moving spine of heat and chemistry, quietly linking tropics to polar latitudes. Arctic sea ice varied through the Holocene as sunlight patterns and ocean heat transport shifted the balance between freezing and melting. Sea ice grows when the ocean loses enough heat in winter, and it shrinks when summer warmth, warm currents, or winds fracture it and expose dark water that absorbs sunlight. Because sea ice is bright, it reflects solar energy and cools the region, creating feedbacks that can amplify small shifts. The ice also insulates the ocean, reducing winter heat loss and changing how quickly new ice can form. Salt is rejected as sea ice freezes, making nearby water denser and encouraging sinking that can help drive local circulation. In some intervals, driftwood, beach ridges, and marine sediments suggest reduced ice, while other intervals show more persistent coverage. These changes affect ecosystems from algae under the ice to top predators because timing of melt controls light and nutrients. Holocene Arctic ice therefore acted as both mirror and gate, regulating exchanges between ocean, atmosphere, and life at the top of the world. Holocene volcanism continued to season the atmosphere with aerosol veils that altered sunlight and temperature for a few years at a time. Large eruptions loft sulfur gases into the stratosphere, where they form reflective sulfate aerosols that cool the surface by reducing incoming solar energy. The stratosphere sits roughly 10 to 30 miles, about 15 to 50 kilometers, above the ground, high enough that these particles can persist longer than ordinary weather clouds. Cooling is usually strongest over land and in summer, when sunlight is most abundant to be reflected away. As the aerosols settle, rain and snow deliver sulfur back to the surface, and lakes and ice layers record the event as a thin chemical pulse. Volcanic ash also adds fresh minerals to soils and seas, sometimes fertilizing growth in nutrient-limited regions. Even when the climatic effect is brief, the geological signal can be clear because sediments preserve the sudden arrival of glassy fragments. In the Holocene, volcanoes reminded the planet that its interior still speaks to the sky. Holocene greenhouse gases stayed relatively low compared with the many earlier epochs, helping maintain an icehouse world with strong polar contrast. Ice cores show carbon dioxide near about 260 to 280 parts per million for much of the late Holocene before modern times, while methane varied with wetlands and monsoon strength. These gases trap infrared heat, shaping the planet's energy balance even when sunlight is unchanged. Small shifts matter because feedbacks amplify them. Cooler oceans absorb more CO2, while warmer oceans tend to release it. Methane responds quickly to waterlogged soils because microbial production rises when wetlands expand and falls when they dry. Dust, sea ice, and vegetation then modulate how much solar energy is absorbed, tying greenhouse levels to reflectivity and circulation. In this background state, glaciers could grow when summers were weak and retreat when summers were strong, paced by orbital rhythms. The Holocene's relatively stable greenhouse levels were not an absence of change, but a balanced conversation among oceans, soils, and air. Holocene fire acted as a recycler, converting stored biomass into gases and ash, and reshaping ecosystems in patterns tied to climate. In dry seasons, lightning ignitions and accumulated fuels can produce wide burns that return carbon to the air as carbon dioxide and smaller amounts of methane. Ash and charcoal then settle into soils and lakes, where they can persist and form long records of past fire frequency. Fire can favor grasses over trees in some regions, shifting surface reflectivity and changing how winds move across the land. After burning, fresh shoots often appear quickly, drawing carbon back into living tissue and stabilizing loose soil. Where repeated fires keep forests open, snow can persist longer on the ground, altering spring melt and local water availability. Smoke aerosols also affect clouds and sunlight, linking a regional burn season to broader atmospheric optics. Across the Holocene, fire served as a moving boundary between growth and decay, helping redistribute nutrients and keep landscapes dynamic. Nitrogen cycling in the Holocene helped regulate the fertility of land and sea. Because life depends on usable nitrogen, even when the air is full of it. Most atmospheric nitrogen is inert, so it must be fixed into reactive forms by lightning or by microbes in soils and oceans. Natural fixation creates ammonia and related compounds that plants and plankton can use to build proteins and DNA. When organisms die, other microbes return nitrogen to the air through denitrification, completing a loop that can tighten or loosen with climate. Runoff carries nitrates to rivers and coasts, where excess nutrients can boost productivity and influence oxygen levels at depth. In the open ocean, cyanobacteria can fix nitrogen in warm, sunlit waters, subtly steering the global balance of nutrients. Nitrogen also interacts with carbon cycling, because growth that draws down carbon requires nitrogen as a partner element. Through the Holocene, this invisible chemistry helped decide which landscapes were lush, which seas bloomed, and how strongly life could tug on the atmosphere. Tectonic motion continued through the Holocene because plates never stopped moving, even when maps look steady. Along boundaries like the San Andreas system, plates slide past each other at rates of a couple inches per year, a few centimeters, storing strain that is released in earthquakes. At subduction zones, oceanic crust dives beneath continents, feeding volcanism and recycling water and carbon into the mantle. These processes build mountains, deepen trenches, and create basins that fill with sediment, quietly changing drainage and coastline shape. Heat flow from the interior also powers hydrothermal circulation on the seafloor, influencing ocean chemistry far from land. Uplift exposes fresh rock to weathering, which consumes carbon dioxide and links tectonics to climate over long spans. Even when a ridge rises only millimeters in a year, the cumulative effect over millennia is a reshaped watershed and a new sediment story. The Holocene therefore sat atop moving machinery, with the solid Earth still rearranging the stage beneath water, air, and living cover. The Himalaya continued rising through the Holocene, and that uplift fed rivers with sediment and minerals that influenced deltas and ocean chemistry. Modern measurements show parts of the range rising a few millimeters per year, roughly 1/10 of an inch, as India keeps pressing into Asia. High relief encourages landslides and strong erosion during monsoon rains, delivering huge sediment loads to the Ganges and Brahmaputra systems. Those sediments build broad floodplains and submarine fans, spreading the mountain's mineral fingerprint far beyond its slopes. Chemical weathering of freshly exposed rock consumes carbon dioxide, while transported clays and carbonates help buffer seawater chemistry. The uplift also steers winds, shaping monsoon intensity and concentrating rainfall on windward flanks while drying leeward basins. In this way, mountain building is not only topography, but also an atmospheric and chemical influence. Through the Holocene, the Himalaya kept acting as a high stone engine, turning collision into sediment and sediment into coastline. Earth's magnetic field continued to wander through the Holocene because the liquid outer core is a restless dynamo. Field strength rises and falls over centuries, and the magnetic poles drift, shifting the regions where auroras are most likely to appear. Minerals in cooling lava and in settling sediments can lock in the direction and intensity of the field at the time they form, creating a timeline of magnetic change. Although full polarity reversals are rare on these timescales, the field can develop complex patches and temporary weakened regions. That complexity matters because the magnetic field guides many charged particles around the planet, influencing how energy is deposited in the upper atmosphere. Changes aloft can affect the chemistry of the ionosphere, which in turn can modify how radio waves and currents would travel through near space. On the ground, magnetism leaves subtle signatures in rocks that help reconstruct motions of plates and past orientations of landscapes. In the Holocene, the field remained an invisible companion, shaped by deep metal motion and expressed as light in polar skies. Modern ocean chemistry still reflects the partnership between life and rock, because organisms continually rearrange carbon, nutrients, and alkalinity in seawater. Plankton in sunlit layers draw down carbon dioxide as they photosynthesize, and some of that carbon sinks into the deep ocean and sediments. At depth, decay returns carbon to dissolved form, while shells and mineral precipitation store carbonates on the seafloor. Rivers deliver bicarbonate and calcium from weathered rock, helping maintain the ocean's buffering capacity against acidity changes. Where upwelling brings deep water to the surface, carbon-rich water can release CO2 to the air, balancing regions of uptake elsewhere. Oxygen levels vary with circulation and productivity, so some basins ventilate efficiently, while others can slip toward low oxygen states. Marine microbes also transform nitrogen and sulfur compounds, shaping which nutrients are available and how trace metals behave. Viewed as a whole, the ocean is a chemical parliament, with currents as messengers and plankton as scribes, continually rewriting the composition of Earth's largest habitat. Earth today rests on the same foundations that shaped its history, with sunlight driving climate, while tectonics and life set long-term boundaries. The planet orbits about 93 million miles from the Sun, roughly 150 million kilometers, establishing the energy budget that oceans and air redistribute. A day of about 24 hours and a tilt near 23.5 degrees organize seasons, winds, and rainfall belts that shape forests, deserts, and ice. Plate tectonics recycles crust, moves continents, and returns carbon and water to the surface through volcanism, keeping the atmosphere connected to the mantle. Oceans store most of the mobile heat, and currents carry it across basins, while sea ice and clouds regulate how much sunlight is reflected back to space. Life, from microbes to forests, acts as active chemistry, accelerating weathering, building soils, and pumping carbon through air and sea. These processes do not compete. They cooperate in feedbacks that have kept liquid water stable for immense spans. The Holocene is only the latest chapter, but the machinery is ancient, and the planet continues to run on its steady cycles. Late Holocene climate records come from natural archives that keep time without ink, such as ice cores, lake mud, tree rings, and cave deposits called speleothems. These archives capture temperature, rainfall, dust, and wind as layered signals that can be dated and compared across regions. In Greenland and Antarctica, annual snowfall compresses into ice and traps bubbles of ancient air, preserving past carbon dioxide and methane. Thin chemical streaks rich in sulfate mark major eruptions, while dust layers hint at storminess and aridity. In lakes, paired seasonal laminations called varves can be counted like years, and pollen grains record shifting forests and grasslands. In caves, stalagmites grow drip by drip, locking oxygen and carbon isotopes into banded stone. Together, these archives let the late Holocene be read as a stitched map of many places and many clocks. By aligning many archives, researchers can separate local weather noise from broader regional and global signals. Late Holocene climate drift was guided partly by orbital geometry, which has slowly reduced northern hemisphere summer sunlight since the mid-Holocene. Earth's tilt and the timing of perihelion change how strongly summers melt winter snow at high latitudes. When summer energy weakens, snow is more likely to persist on polar margins and in mountain cirques, brightening the surface and encouraging additional cooling through reflectivity. This forcing unfolds over thousands of years, so it acts like a quiet bias rather than a sudden shove. Oceans and atmospheres translate that bias into regional changes because currents and winds decide where heat is stored and released. A small shift in summer melt can alter glacier mass balance, lake levels, and vegetation belts. Orbital pacing does not dictate every year's weather, but it sets the background stage on which shorter rhythms play. The redistribution of sunlight is unequal between hemispheres, so the same forcing can create contrasting patterns in different oceans. Neoglaciation is the late Holocene tendency for glaciers to regrow in many regions after earlier warmth, and it is recorded in moraines that step down valleys like stony shorelines. As summers cooled slightly, snow lines lowered and small ice fields expanded, especially in high mountains and subpolar coasts. Glaciers advanced, paused, and retreated in pulses, each pulse leaving ridges of boulders and gravel that can be dated by buried soils, tree remains, or exposure clocks on rock surfaces. A glacier is both climate and conveyor. It grinds bedrock into fine flour and delivers that sediment to rivers and lakes. Meltwater pulses reshape channels, while the ice's weight depresses crust and then releases it during retreat. Even a modest advance can bulldoze forests and redirect drainage, turning a temperature trend into a rearranged landscape. In these ridges, late Holocene cooling becomes visible ground. Lichen growth and the first returning trees on fresh moraines also provide clocks that anchor the timing of ice movement. The medieval climate anomaly and the Little Ice Age were late Holocene intervals that show climate can vary noticeably without leaving the icehouse state. From roughly 950 to 1250 CE, some regions around the North Atlantic experienced relatively mild conditions, while other areas followed different patterns, proving the atmosphere is not a single uniform blanket. From about 1300 to 1850 CE, many mountain glaciers advanced, and winters were often harsher in parts of the northern hemisphere, with sea ice changes and storm tracks shifting in response. These intervals were shaped by multiple influences acting together, including volcanic aerosols, solar variability, and internal ocean-atmosphere dynamics. The signal appears in glacier moraines, tree ring widths, lake sediments, and historical observations, but it is patchy in space, as climate always is. The late Holocene shows that regional climates can swing, while the planet's long-term machinery stays the same. Glaciers in the Andes and New Zealand also show advances and retreats, even when the exact timing differs from the North Atlantic. Large volcanic eruptions in the late Holocene cooled climate briefly by lofting sulfur aerosols into the stratosphere, where they reflect sunlight back to space. When an eruption injects sulfur dioxide above weather systems, it can spread a thin veil around much of the globe and persist for 1 to 3 years. The 1815 eruption of Tambora in Indonesia is a well-studied example, followed by widespread cooling and unusual weather in 1816 that appears in tree rings and ice chemistry. Earlier events, such as the 1257 eruption of Samalas, also left strong sulfate spikes in polar ice. The cooling is typically stronger over land than ocean, and can shift rainfall belts by changing temperature gradients. Ash adds minerals to soils and lakes, while aerosols change the color and clarity of sunlight. For a brief span, the deep Earth writes directly on the sky. Because the stratosphere sits roughly 10 to 30 miles, about 15 to 50 kilometers above the ground, its aerosols travel far before they fall. Solar variability subtly influenced late Holocene climate, and its fingerprints appear in isotopes like carbon-14 in tree rings and beryllium-10 in ice. When the sun's magnetic activity strengthens, it deflects more cosmic rays, reducing the production of these isotopes in the upper atmosphere. When activity weakens, cosmic rays penetrate more easily and isotope production rises, creating measurable changes that can be dated year by year in some records. The climate effects are modest compared with large volcanic eruptions, but they can matter through feedbacks involving sea ice, stratospheric circulation, and regional storm tracks. Solar minima such as the Maunder minimum in the late 1600s coincide with cooler conditions in parts of Europe and the North Atlantic region, though causation is not single-threaded. The sun sets the budget. Small variations can still tip the balance in sensitive seasons. These isotope curves also help reconstruct solar storms and long changes in Earth's magnetic shielding through time. The North Atlantic Oscillation shows how the ocean and atmosphere can rearrange heat and storms without any external push. It reflects shifts in the pressure difference between the Icelandic low and the Azores high, which steer westerly winds and winter storm tracks. When the pressure difference is strong, milder and wetter winters often reach parts of northern Europe, while Greenland and northeastern Canada can become colder and drier. When it weakens, cold air can spill farther south and storms take new routes across the Atlantic. These wind changes influence how quickly the ocean loses heat, affecting deep water formation and the strength of the overturning circulation. Sea ice responds as both mirror and lid, changing evaporation and momentum transfer between air and sea. The oscillation turns geography into weather, then weather back into ocean structure year after year. Its positive and negative phases are like alternate routes for wind, each with its own temperature and precipitation signature. Pacific variability, including the El Niño Southern Oscillation, shaped late Holocene droughts and floods across large parts of the world. During El Niño events, weakened trade winds allow warm surface water to spread eastward, shifting tropical rainfall and sending atmospheric ripples into distant continents. During La Niña, stronger trade winds enhance upwelling of cool, nutrient-rich water in the eastern Pacific and shift rainfall in the opposite direction. These swings influence marine productivity because upwelling feeds plankton blooms that draw carbon from surface waters. They also influence fire seasons and river flow by steering storm tracks and monsoon strength. Coral skeletons preserve these changes as chemical banding, and lake sediments record them as alternating wet and dry layers. The Pacific is a wide basin, but its mood can reach across the globe through air currents that carry heat like news. In Australia, Indonesia, and parts of the Americas, these shifts can mean the difference between reservoir-filling rains and long, dry seasons. Late Holocene sea level changes were small compared with deglaciation, yet even shifts of a few feet, a meter or two, can transform coasts and estuaries. Global mean sea level approached modern values as major ice sheets stabilized, but regional sea level continued to change because land itself moves. Isostatic rebound lifts formerly glaciated regions, while sediment loading and tectonic subsidence lower others, creating different relative sea level trends along different shores. River deltas can sink under their own weight, while some rocky coasts rise as the mantle slowly relaxes. Storm frequency and wave climate decide whether a shoreline advances by building beaches or retreats by eroding bluffs. Salt marshes and mangroves track these changes closely, migrating landward when space exists and drowning when it does not. In this way, a small global signal becomes many local coastlines. Tide gauges, coral terraces, and salt marsh peats each provide pieces of the puzzle, building local sea level curves from living and sedimentary evidence. Late Holocene storms reshaped coastlines by moving sediment in sudden bursts, leaving overwash layers and surge deposits that remain visible for centuries. A single cyclone can push seawater far inland, carrying sand and shells over barrier islands and into back barrier lagoons. Those sand sheets become timestamps in marsh mud, distinct from the darker organic layers above and below. In higher latitudes, winter storms can carve cliffs and shift gravel bars, changing harbour shapes and inlet positions in a matter of days. Storm waves also stir the shallow seafloor, resuspending nutrients and altering coastal food webs. Where dunes are breached, wind begins building new ridges, so the coastline heals itself in slow, layered construction. Over centuries, repeated events sort grains by size and density, sculpting long spits and barrier chains that look steady only from far away. The sea rights quickly when the wind lends it power. Then the calmer years resume. Rivers in the late Holocene rebuilt their floodplains through avulsions, the sudden jumps of channels from one course to another. As a river lays down sediment, it raises its bed, and a raised bed becomes unstable during large floods. When a breach occurs, water finds a steeper path and the river may abandon its old channel, carving a new one across the plain. This process builds delta lobes, fills back swamps, and creates a mosaic of soils that differ in grain size and fertility. The Mississippi, the Yellow River, and the Ganges Brahmaputra are well known for such behavior. But the mechanism is universal wherever rivers carry heavy sediment loads. Avulsions alter wetlands, change salinity intrusion, and redirect nutrient delivery to coastal seas. They also leave abandoned channels as oxbow lakes and buried sand bodies, building a three-dimensional memory beneath flat ground. A river is never only a line, it is a moving decision. Holocene coral reefs and carbonate shelves acted as natural gauges by recording temperature, sea level, and seawater chemistry in their growth bands. When conditions are favorable, corals and coralline algae build rigid frameworks that trap sand and create sheltered lagoons. Over centuries, reefs can accrete fast enough to track gradual sea level change, and their internal layers preserve shifts in growth rate and seawater composition. Oxygen isotopes and trace elements in coral skeletons reflect the temperature and salinity of the water in which they formed. Reefs also reshape local currents by creating barriers and channels, changing where sediment settles and where waves break. When storms strike, broken coral fragments become beach sand, turning living architecture into mobile grains that later cement into limestone. In this way, life engineers the coastline while quietly writing a chemical diary of the sea. The reef is both builder and historian. Some massive corals lay down near annual bands, so their skeletons can be read almost like calendars. Permafrost and high-latitude peatlands in the late Holocene stored immense carbon reserves, linking frozen ground to atmospheric chemistry. In Arctic and subarctic regions, cold soils can lock organic matter away for thousands of years because microbes work slowly in low temperatures and often low oxygen. Peat accumulates where waterlogging limits decay, building dark layers that can reach many feet, several meters, thick. Ice wedges and frozen lenses shape the ground into patterned polygons, guiding drainage and creating small ponds that further favor peat growth. When summer's warm, the active layer deepens, allowing more decay and shifting the balance between carbon dioxide and methane release. These changes can be patchy because vegetation, snow cover, and soil moisture vary across short distances. Yet the total stored carbon is large enough that the frozen north acts like a vast vault in the Earth system. In the late Holocene, that vault remained mostly closed, but it never stopped interacting with climate. Wildfire regimes in the late Holocene responded to climate swings by shifting the timing and intensity of burns across continents. Dry years increase fuel flammability, and wind patterns decide whether ignitions stay local or become sweeping fires. Fire changes the land's reflectivity and roughness, and it reshapes nutrient cycles by converting wood into gases, ash, and charcoal. Charcoal is especially important because it can persist in soils and sediments for long spans, storing carbon in a durable form. Post-fire landscapes also erode differently because vegetation that once held soil in place is temporarily reduced. That can increase sediment delivery to rivers and lakes, leaving distinct layers that coincide with fire histories. Fire is therefore both an atmospheric event and a geological one, moving carbon through air while moving minerals through water. In the Holocene, flames acted as a fast messenger inside slower climate rhythms. Lightning leaves little behind, but charcoal layers do, and they let fire history be tracked across millennia. The late Holocene stored enormous energy resources underground in the form of coal, oil, and gas, which are the long compressed remnants of ancient ecosystems. Coal largely comes from peat-forming swamps of the Carboniferous and later periods, while petroleum often forms from marine plankton and algae buried in oxygen-poor sediments and transformed by heat and pressure. Over millions of years, organic matter becomes hydrocarbons that migrate into porous rocks and accumulate beneath impermeable seals. Salt layers, shales, and tightly cemented limestones can serve as lids, keeping the fluids trapped until drilling or natural leakage releases them. This storage is a geological time capsule of ancient sunlight, because photosynthesis built the organic material that later became fuel. The presence of these reservoirs depends on basin shape, sedimentation rate, and the temperature history of burial. Long before human use, the planet had already filed away energy in deep strata, waiting in darkness silently. By around 12,000 to 10,000 years ago, near the start of the Holocene, agriculture became possible in several regions because climates and river systems were comparatively stable. Predictable seasonal rains and steadier sea levels allowed floodplains to build rich soils and sustain repeated harvests. In the Fertile Crescent, the Nile Valley, parts of China, and other centers, people domesticated cereals and animals, turning seasonal growth into stored food. This was also a planetary change in land cover, because fields replaced diverse plant communities and grazing altered grasslands. Clearing and tilling exposed soil to wind and water, increasing erosion in some places and building thicker valley sediments in others. Irrigation spread moisture into dry seasons, but it could also raise salinity as water evaporated and left minerals behind. Over centuries, agriculture became a geomorphic force, subtly redirecting carbon, nitrogen, and water through the same cycles that shape wild landscapes across wide valleys. Early cities grew where water could be managed, and their rise made rivers into engineered systems that altered deltas, floodplains, and sediment delivery. Canals, levees, and reservoirs redirected flow, sometimes reducing frequent floods locally, while increasing the risk of rare catastrophic ones when structures failed. Irrigation expanded cultivation into drier areas, but it also brought salts to the surface as water evaporated, changing soil chemistry and forcing shifts in crops and settlement. Urban demand for bricks, pottery, and metal increased quarrying and fuel use, moving rock from one place to another at a scale earlier villages rarely reached. River channels were straightened, embanked, or diverted, changing how nutrients reached coastal seas and how wetlands grew. Even the act of concentrating people in one place reshaped local microclimates through smoke, shade, and altered albedo. Cities became new kinds of landforms, built from sediment and sustained by flow. The river, once free to wander, learned the hard edges of walls. Metallurgy expanded human influence by linking mining, smelting, and forests into a chain of earth moving and combustion. Copper and later bronze required furnaces, and furnaces required charcoal, tying metal production to woodland cutting in many regions. Ironworking, widespread in many places after about 1200 BCE, demanded higher temperatures and often greater fuel supplies, intensifying pressure on nearby forests. Mining reshaped hillsides by exposing fresh rock, building spoil heaps, and redirecting streams for washing and transport. Smelting released metal-rich fumes and fine particles that settled into soils and lake beds, leaving detectable traces in sediments and even in some ice. Over time, roads and trade routes stitched ore districts to ports and plains, moving concentrated geology into tools, weapons, and infrastructure. In Earth system terms, metallurgy accelerated the movement of elements from crust to atmosphere to sediment, compressing long geochemical loops into human time. Stone and fire became partners in extraction. The industrial era transformed the human imprint by rapidly releasing fossil carbon that had been stored underground for tens to hundreds of millions of years. Coal, then oil and natural gas, became dense energy sources that powered engines, transportation, and large-scale manufacturing. Burning these fuels converts carbon into carbon dioxide, and measurements show atmospheric CO2 rose from about 280 parts per million in the pre-industrial era to over 420 parts per million by the early 2000s. Alongside CO2, combustion and industry release aerosols and reactive gases that influence clouds, sunlight, and air chemistry. Rivers were dammed, cities expanded, and mining moved billions of tons of rock, turning human work into a measurable geological process. The ocean absorbs much of the added heat and a large fraction of the added CO2, changing seawater acidity and carbonate balance. In a single century scale burst, carbon that took ages to bury returned to the atmosphere, and Earth's climate system began responding within decades. In the present day, Earth is studied as a connected system using satellites, ocean floats, ice cores, and global sensor networks that reveal change in near real time. Satellites measure sea surface height, ice extent, vegetation greenness, and atmospheric gases, turning the planet into a monitored sphere rather than a set of distant regions. The Argo float array, with thousands of drifting instruments, profiles temperature and salinity through the upper ocean, showing where heat is stored and where currents rearrange it. Ice cores extend the instrumental record backward, letting modern measurements be compared against tens of thousands of years of trapped air. Many scientists use the term Anthropocene to discuss whether human-driven changes now leave a distinct signal in sediments and chemistry, though formal geological definitions are still debated. What is not debated is the continuity of process. Oceans, air, rock, and life still trade matter and energy, and humans now participate as a late-arriving agent within those ancient exchanges. The modern rise in atmospheric carbon dioxide is recorded with unusual clarity because it is measured directly and also preserved in natural archives. In 1958, continuous observations began at Mauna Loa in Hawaii, and the steadily climbing Keeling curve became a signature of the industrial age. Ice cores add long context by trapping ancient air bubbles, letting the last many thousands of years be compared against recent decades. The carbon carries an isotopic accent, Fossil fuels are relatively depleted in carbon-13, and that fingerprint appears in modern air as these fuels are burned. Oxygen in the atmosphere has also declined slightly, consistent with combustion. The scale is stark when expressed simply. About 280 parts per million before large-scale industrialization, and over 420 parts per million in recent years. A once-buried treasury of carbon has been moved back into the sky, and instruments now watch it rise day by day. It is a number etched into air and ice. Aerosols rose alongside greenhouse gases, and their influence is intricate because they can cool by reflecting sunlight, even as greenhouse gases warm by trapping heat. Sulfate particles from coal burning and some industrial processes brighten clouds and increase Earth's reflectivity, while black carbon from incomplete combustion darkens snow and ice, helping them absorb more sunlight. Because aerosols tend to remain aloft for days to weeks, their strongest effects are regional, clustered near and downwind of major sources. The same city plume that shades a summer afternoon can also seed clouds and alter where rain falls. When regulations reduce sulfur pollution, the temporary cooling mask can thin, revealing more of the underlying greenhouse warming. Volcanic aerosols add natural pulses to this story, but modern industry has made aerosols a recurring ingredient of the sky. Here, air becomes a workshop where tiny particles decide how bright the planet looks from space. Their lifetimes are short, but their reach is wide. Human land use reshaped the carbon and water cycles by converting forests, grasslands, and wetlands into fields, pastures, and managed landscapes. Clearing trees reduces stored carbon in wood and soils, changes surface roughness, and often decreases local evaporation, which can influence clouds and rainfall downwind. Irrigation adds another twist by moving water from rivers and aquifers onto dry ground, cooling the surface locally while concentrating salts in some soils as water evaporates. Modern fertilizers intensified these changes by adding reactive nitrogen at vast scale, especially after industrial ammonia production expanded in the early 20th century. Extra nitrogen boosts yields, but it also leaks to rivers and coasts, where excess nutrients can fuel oxygen-poor waters. Some nitrogen returns to the air as nitrous oxide, a long-lived greenhouse gas. In many regions, terraces and canals remade hillsides. In this way, farming became a planet-scale rearrangement of elements, tying sunlight, soil, and chemistry into new loops. Rivers have been engineered so extensively that many now deliver less sediment to the sea, altering deltas and coastlines that rely on continual replenishment. Dams slow water and trap sand and silt in reservoirs, building underwater deltas behind the dam wall while starving the coast downstream. A single large reservoir can hold back millions of tons of sediment each year, shifting shoreline behavior over decades rather than millennia. Levees keep rivers in fixed channels, preventing seasonal flooding that once spread fresh mud across floodplains. That mud was a natural scaffolding for wetlands and a slow defense against sinking ground. When sediment supply falls while land subsides, deltas become vulnerable to storms and salt intrusion. Channelization also speeds water toward the sea, changing how nutrients and organic matter are processed along the way. In the modern era, many coasts are not only shaped by waves and tides, but by upstream decisions written into concrete and steel. The ocean has absorbed a large share of human-released carbon dioxide, and this uptake has measurably shifted seawater chemistry toward greater acidity. When CO2 dissolves in seawater, it forms carbonic acid, which changes the balance among bicarbonate, carbonate, and hydrogen ions. Since pre-industrial times, average surface ocean pH has fallen by about 0.1 units, from roughly 8.2 to about 8.1, a small-looking number that represents a significant increase in acidity on a logarithmic scale. Lower carbonate availability makes it harder for corals, some plankton, and many shell-forming animals to build and maintain calcium carbonate structures. The effect is not uniform because cold waters absorb more CO2, and upwelling can bring naturally carbon-rich water to the surface. Still, the direction is consistent. The sea is taking in carbon, and its internal chemistry is adjusting in response. In marine sediments, this adjustment will be recorded as a quiet shift in what dissolves, what grows, and what endures. Ice and snow respond quickly to shifts in heat, so the cryosphere has become one of the most visible witnesses of recent change. Mountain glaciers have retreated in many regions, exposing fresh rock and forming new lakes behind moraine dams that were once stabilized by ice. Satellite records since the late 20th century show strong year-to-year variability in Arctic sea ice, alongside a clear long-term decline in late summer extent. Earlier spring melt alters river timing, affecting ecosystems and water supplies far downstream. As land ice loses mass, global mean sea level rises, and since around 1900 the increase totals roughly 8 inches, about 20 centimeters, though the rate varies by era and region. Warmer ocean water expands as well, adding its own contribution. The cryosphere also influences ocean circulation by changing freshwater inputs, which affects salinity and density at the surface. Ice is not only scenery, it is a regulator of light, water, and the pace of the sea. Cities have become a new kind of surface, turning rock into asphalt and concrete that store heat by day and release it by night. This creates urban heat islands, where nighttime temperatures can be several degrees higher than nearby rural areas, and the contrast is visible in thermal imagery from aircraft and satellites. Urban growth also seals soil, reducing infiltration and increasing runoff, which can intensify flooding during heavy rain. Water demand concentrates around cities, leading to aquifer drawdown in some regions and land subsidence that subtly changes drainage and coastal relative sea level. The materials of cities alter chemistry too, because concrete weathers and can influence the alkalinity of runoff, while roadside dust carries metals into streams. At night, artificial light outlines the continents like a new kind of aurora, revealing where people have clustered on the planet's skin. The metropolis is an ecosystem of stone and energy, and it has become a visible layer in Earth's surface story. New materials have entered sediments as durable markers of modern civilization, and plastics are among the most widespread. Produced at large scale since the mid-20th century, plastics fragment into microplastics that travel in rivers, drift in ocean currents, and settle into seabeds and lake bottoms. These fragments mingle with natural grains, creating layers that future geologists could recognize without any written record. Another distinctive signal comes from fly ash spheres formed in high-temperature combustion, which fall as fine dark beads into soils and mud. Radioactive isotopes from atmospheric nuclear testing in the 1950s and early 1960s also provide a sharp global timestamp, because they spread widely and became locked into sediments and ice. even the chemistry of fertilizers and industrial metals can leave persistent traces. Some beaches now contain plastic sand among shells. Earth has always written history into layers, and now those layers carry polymers, ash, and atoms rearranged by human hands. Earth in the present day is the same interconnected system it has always been, but it is now observed with a clarity earlier ages could not imagine. Satellites track sea level, ice, clouds, and vegetation in near real time, while ocean floats profile temperature and salinity through the upper miles, the upper few kilometers of the sea. These measurements show ancient pathways still operating. Currents still carry heat, winds still steer moisture, and plates still recycle carbon and water through volcanism and subduction. Life remains a chemical force, building soils, pumping carbon through the ocean, and shaping the composition of the air. Humans have become a late, concentrated agent within these cycles, moving carbon from rock to sky and rearranging rivers, coasts, and land cover. The story up to now is not a tale of stillness, but of feedbacks responding to new inputs and new constraints. Earth's history is a continuous manuscript, and the present chapter is being written with instruments, cities, and the same sunlight that began the story. In the last sliver of time, humans appear as late builders of their own kind of terrain. Fields spread, rivers are guided, metals are drawn from hillsides, and buried carbon is brought back into the atmosphere with a speed the rocks do not usually know. The ocean takes in heat and dissolved carbon, reefs and coasts respond, and instruments in orbit and in the sea watch these changes as they unfold. Yet the planet remains the same connected system it has always been. A living exchange between mantle heat and sunlight, between salt water and rain, between drifting continents and the breathing surface. Earth does not keep a single still face. It keeps a continuity of motion. If you enjoyed these quiet explorations, consider subscribing so you can easily return here whenever you need to rest. For now, let the immense timescale settle around you like a calm horizon, and let the planet's long, steady processes carry the night forward. Sleep well.